So we're going to find out. I just estimated it, you know, in my head at around 10 millihenries.
Okay.
Okay. And then this is representing the collector voltage, right? Let's see. Let me punch this. There's the collector voltage, and we'll bring it out here and show you what that would look like in the self-oscillation. And then this is the collector current, and this is what it would look like close up. It's a small duty cycle, high current, high voltage. So, you know, at the peak power here, you're looking at 200 volts at a third of an amp, so that's about 60 watts, right? But that's 60 watts at a small duty cycle, so when you take the duty cycle into account, you're only looking at a couple of watts, right?
So that's to be expected with all classical models, is that we're getting very high voltage for very low watts.
Well, this is sort of fictitious because on a 3055, the one that was shown in the thing on the web, 3055s break down at 100 volts. So at 100, it wouldn't do this. It would start breaking down the transistor. The other problem with this model here, this is a blocking oscillator. That's what has been presented as a way of self-oscillating this coil. And that's cool, but the impedance matching of the coil to the base is not optimal for energy transfer. So in fact, there should be a single winding going through there. Where you've got 12 windings, there should be a single winding going back through there to just drive the base. That way, the amount of energy that's required to run the base is a relatively high current at low voltage. Right now, that coil and this coil are in parallel and at the same number of turns. So the base is being driven through a resistor, a limiting resistor. So this is sucking up power, and so is the base drive. So ideally, the way that you would probably want to drive this is to run a single wire along with the rodent winding, and then use that to drive the base of the transistor, if in fact this was the type of thing that you were going to do, right? In fact, what we might do on the experiments here is to thread a wire through there and drive that from the pulse generator, and then see what the excitation on the coil is like with an independent frequency, not self-synchronized, but tuned so that we can reach the peak output on the device and see what we get. Okay. Cool. So anyway, this is your first order simulation. Then I played around with a few others, just to see.
Could you explain a bit what's going on to us? Again, sorry.
Yeah, this is. And by the way, the reason that I use the older scopes, the old vacuum tube scopes, is that a lot of the work that I've done in the past has been in high voltage, high frequency fields. These scopes are a little affected by odd fields, where a lot of the modern solid state scopes get wiggy when you put high voltage, high frequency fields in. Okay, now what are we going to do as he edits?
It's very loud, your things.
What, the microphone?
Yeah, I don't know how to turn it down.
Don't know.
No, it's
okay. Oh, I see. Well, it's my voice. I'll turn it down a little. Turn it down.
Okay, no, it's alright.
How's that?
Yeah, it's fine.
Well, it is hitting large peaks.
Okie doke. So, what have we got here?
So if you come in this way,
okay.
what we've got is a pulse generator. This only goes up to about 1 megahertz or so, feeding into a pulse amplifier that's able to put out an amp at a handful of nanosecond rise time. And it has a relatively high voltage compliance, about 100 volt voltage compliance. So what we're doing is we're simply creating right now we're creating a 50 volt pulse of 100 nanoseconds at 1.0976 megahertz, right? Which is 1/3 of the resonant frequency of the coil.
Pulsing it into the...
We're pulsing the two wires that originate at the equator of this coil. The ends of the coils are sitting in free air outside. It's sitting on styrofoam. The table's an aluminum table with slots so it doesn't create eddies. And it has little magnetic, no magnetic effect appreciably. And the scope probe up here has got a small piece of copper wire coming down to simply sniff the end of the coil without contributing any loading capacitance to it. And then that's displayed over here on the oscilloscope. And what you can see is a waveform. When we hit the third harmonic of the generator frequency, we see it peaking. And we know that the resonant frequency of the coil is going to show up as an odd pulse in a sequence. So you see the odd pulse, and then 2, and then odd, and then 2, and then odd, and then 2. And this is the pulse ringing the bell at 1/3 the resonant frequency of the coil. So we know the resonant frequency of the coil. We can sweep through this and get peaks at 5th harmonics and 7th harmonics and so on. But it's most convenient just to, take a very sharp, very narrow pulse and inject that into the resonant swing of the coil. And at just the right phase angle, you get a peaking of the voltage on the coil at the ends, which we're looking at with this little piece of wire. And let's see, and this is a 10x probe, so sitting out here with just a couple of, maybe a fraction, not even a couple, it's maybe a fraction of a picofarad. We're looking at 40 volts peak to peak, right? Which means that the voltage sitting out on that wire is well over a kilovolt. Okay. So one of the things that we're going to do next is we're going to hook up a voltmeter, an electrostatic voltmeter, that's able to see up into the megahertz, and see if we can read that voltage directly. The capacitance of the meter will load the coil bit, but we should be able to get a true RMS voltage readout of the coil. So not a peak readout, an RMS readout, right? And then by looking at the waveform, we should be able to determine what the peak voltage is coming out of that coil, looking into one of these voltmeters. So that was the next thing we were going to do.
So could you describe in the most simple terms?
What have we done?
Like
we're ringing the bell.
We're ringing the bell. So we're getting
bell.
it into a resonant frequency, but how much is going in, and is there anything anomalous coming out at this stage?
No, nothing anomalous coming out. What we have is a resonant coil with a fairly high Q, and that may be due to the fact that we've used a Litz wire to wind this coil. The Litz wire is 120 strands of number 42 wire. Okay, so that's, if you sat here and counted all the strands, that's what you get. And then these strands, like a true Litz wire, every inch or so come to the surface. So the bundle isn't just a twisted set of wires. The wires keep emerging to the surface and diving back into the bundle periodically, which is what makes a Litz wire a Litz wire. And by doing that, you distribute the current in the wire through all of the portions of the wire instead of being on the outer surface alone. So the series resistance of this type of wire at high frequencies is significantly less than a solid piece of wire where most of the current is involved in the skin effect on the surface of the conductor, right? So you'll always get a much higher Q in the frequencies of less than 10 megahertz with wire like this. Okay. So now we can goof around with voltmeters and see what we can do with that. I think I want the kilovolt meter.
Can I film it? Is it okay?
It's fine, but I'm just going to
You
be
sure?
for a while.
But what do you think of all this?
It's good.
Yeah.
He has good
Voltmeters.
technical background.
500.
Years of experience of this. He has a lot of good toys.
1 kV.
Good old stuff. Huh?
Yeah, look at all this.
1 kV. We may have to also get another one of these voltmeters from upstairs. And the capacitance of this voltmeter is 59 picofarads. So what I'm going to try and do is reference this. So we need a ground reference first. And I guess that would be best done.
So what's your day job? What do you do?
What's that?
What's your day job? What do you do during?
I have two things.
Yeah.
I design, repair, modify amplifiers for rock and roll musicians, and I design and build and assist in a research group on electron beam microscopy for semiconductor industry. So a lot of the work that I've done over the last 18 years has been in electron and particle beam systems. So, and before that, it was a lot of plasma systems for the semiconductor industry. So now let's see if we can actually see something on here. We're going to have to re-resonate this because the loading capacitance is going to cause a shift in the frequency. Whoa. Okay, let's go knock down one.
Franklin, is there anything special about these grooves in the
What's that?
in the bit of plastic separating these two coils? They're these.
Yeah,
What is that?
it's meant to wind another smaller conical coil
Oh, an exciter.
inside, and we bring the wires out through
Yeah.
the grooves.
Yeah. Okay, now.
So what you doing?
I'm trying to tune it so that I can get some voltage across this thing. And let's see what it does. I mean, right now there's about 100 volts across it at a loading capacitance of about 60 pF. Okay. Now, but it's on the other end. Oop. Limit.
So this is what you've been doing a lot of, is tuning it up, right?
It's just a tedious thing of tuning. So that's too much load on this coil. 60 picofarads is a huge load on that coil.
So what is that in volt and amp terms?
Huh?
What is that in volts and amps terms, in watts?
Well, it's not a matter of watts or volts or amps. It's just a matter of
Oh, sorry.
you can't it's not going to develop much voltage.
It's the load you're talking about.
I mean, right now it's just developing about 100 volts at that much loading capacitance. I'm going to take a look at it and see what it looks like directly. Because the loading capacitance of the probe is only about 7 picofarads. Whoa, shit. Okay.
So what are the parameters you're changing as you tune it?
I'm just shifting the frequency to see, you know, like right now we've got a couple of 100 volts coming out of it, and that's about it. There's about 400, almost 300 peak to peak. Okay. And we're going to go down a slightly narrower duty cycle. If we okay. 100 nanoseconds. What's the period on that? There it is. One, two. That's the third harmonic, so we're there. sure if we can get to 1.5. Now, it's the resonance on this coil with a 100 nanosecond pulse at 1.08 megahertz, so that third harmonic of this would be 3 megahertz, 3.25 megahertz.
108 is the Tibetan lucky number.
Huh?
108 is the Tibetan lucky number.
Is that right? Okay. That's good. Okay. So that's just with the scope probe on there. So now, okay, so we have a total of 200, we got 1, 2, 3, 6, 700 volts peak to peak with a just a 50 volt excitation pulse at the bottom, which is, I suppose, is not too bad for a coil of that size. So that's 50, 750, and you've got two coils bucking each other. So 50, 12515. So it's a Q, an evident Q of about 15 with this setup.
What's a Q?
The Q is the amount of energy stored over the amount of energy dissipated in the system. And I'm going to come down and look at the pulse itself that's driving the base. And that pulse is a small pulse of 50 volts. That's what we thought. And that's what the pulse looks like going into the base of that coil.
So that's going in an alternating current.
You see the little ripple on there?
Yeah.
Okay, that's the resonance of the coil feeding back to the pulse generator.
Wow.
Right? And oh, gotta get this up here. So what you see there is a no, it's there. So now we're back up to the almost 108. See the ripple in there? That's a resonant frequency. And it's strong enough that it's feeding a back current into the pulse generator. Pulse generator's got an amp of current capacity. This coil at resonance, if it had an appreciable resonance, the base of the coil would be modulating the current feeding it, right? And so its current is now reflected across the 50 ohm resistor, and the magnitude of that one is 0.5. So we're about there we go. We're about 0.2 volts. 2 volts at 50 ohms. So we're at about 40 milliamps of reflected current off of the base of that thing. So that's 40 milliamps of base current. What do we say the voltage was, peak to peak? 700, so that'd be 350. Peak root 2 times that is what? Oh. I gotta get my bloody... No, I've got it here. It's nice. There's I can load my HP11 on my iPhone now. It's a lovely thing. Okay, so I've got 350 divide about 247 4x. So you were looking at about how much power is that going into that thing? Hold on.
I love the way the closer you get to it, it changes the effect.
Oh yeah, that's. I mean, your camera is a capacitor. You're a capacitor. We're all capacitors in this world. So, let's see, 0.04. So we've got a little less than 1/10 of a watt, about 80 milliwatts going into the coil, right? So we've got 80 milliwatts going into the coil and producing a 350 volt peak waveform out of there, which is not too damn bad for a piece of wire with no core. And I'm not clear about what the physics of the neutron is, but in all of the free energy stuff that I've looked at over the years, there are these fundamental principles that seem to eke out of the ones that had the highest probability or greatest number of witnesses to their very existence. And the characteristics that were involved were that the devices were periodic, that you would excite them and then they would relax, and then you'd excite them and they'd relax. So you go through this impulse function. And if you look at the work that Tesla did, what he was doing with his light bulb exciters and all of that, the little transformers that would oscillate, is he was creating, he had actually generated the first pulse width modulated resonant voltage converters ever, right? And when you phase the pulses at the right phase angle to the resonant sine wave that's being generated, you can transfer all of the energy into the resonant system with none of it coming back. And this is that art of impedance matching, which he was quite good at. And the same principles seem to apply to a lot of these types of devices, that if you can create impulse functions that allow the device to, for one reason or another, defy what we know as a classical physics and excite the medium around it, and in the relaxation pull in energy from the surrounding area, then that is a mechanism that explains why an over-unity device could possibly exist, right? So whether you're sucking in tachyons or what, nutrient, we don't know, right? But a friend of mine and I, years ago, decided that we would sit down. I wish I had the notebook now, but we decided to figure out how much energy is in a cubic meter of space. And conservatively, with the number of mechanisms and energy fields and waves going through a cubic meter, we came out to something like 50,000 watts per cubic meter. So if in fact you could extract energy from the vicinity of an oscillating system that's going through some periodic expansion and collapse, and affecting those things or the fields around it, then in a cubic meter you could power an awful lot of houses very conveniently.
Inexhaustibly, or?
Pardon me?
Is that energy inexhaustible? I mean,
it's inexhaustible. It's everywhere. I mean, this whole bloody universe is being powered on a regular basis. So. And there's these little hooks out there, like all of the suns in the universe all radiate at the same frequency. And whether or not they're synchronized or not, I'll be damned if I know. But and you know, and then there's also the idea that some people are one of Hawking's buddies, what's his name? We just saw him recently, and he had explained that they were looking for gravity waves, and I personally don't believe they exist, because from everything that I've been able to extract from what I've read, gravity is one of those things that is instantaneous throughout the universe at all points. So since you could do that, that starts to suggest that there's a lot of other things that you can do that have nothing to do whatsoever with time, right? And this is one of those things that if, for instance, you had a match and you took all of the mass in a match and exhausted it over the period of a year, you could get a great deal of energy out of that match. You could warm your house, right? But if you extracted all of the energy from the mass of a match in about 10 microseconds, you would take out a very large section of San Jose because of the expenditure of the energy. And so it's not a matter of how much energy is there, it's how much energy you can extract per unit time, right? And the more that you can excite the space around something in a large volume, the more you can pull out. There's always the danger that the mechanism that you use could not handle the amount of energy coming out of the space around it, and then you have a problem. And that seems to have also come up in the literature from time to time, where these things don't behave properly and melt down. They don't go nuclear because you can't, but they do collapse. And I would love to see one do that. But I haven't seen one do that.
So what we're seeing here, are we seeing any more energy being put out than
we're not seeing any more energy being put out than we're putting in, no.
Did you expect to see that, Franklin, at this stage?
No.
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 So what needs to happen to the neutron development before it can...
I don't understand.
start
Well,
to
you know,
accumulate
in the neutron, there's another gentleman named Sweet, who had, Floyd Sweet, yeah.
Okay.
And Floyd Sweet was convinced that the assembly of coils that he did, which were maybe similar to Bedini, Hendershot, and all of these, what he did is he produced these coils which were like this, a Litz wire, right, and terminated one end, and then came back down to wherever all the wires start, separated them into two bunches, right? And he had an input and an output on this bunch of wires. Then he sets this thing into a magnetic field and excites it cross field with another set of coils. And you know, I looked at that and I thought, well, what the hell is this man doing? And one of the curious things that he does is that when you put it in a magnetic field, you bias the conductors so that the electron flow tends to be greater in one direction than the other. And it may in fact be that when you excite things that way and then pump it from the side, that the coupling between something that's not magnetic at all now has a magnetic characteristic simply because of the biasing field. And again, his device is another one of these that you have to pump from the side. And then once he had, you know, he has some other tricks that he puts in there, like training the magnet to remember the frequency and things like that, which I'm not clear on yet. But this has a characteristic similar to that, in that you've got wires moving in the same direction and returning in the same direction. So the field at each end, instead of being a bipolar field, is a monopolar field. I don't know what that has to do with the price of eggs in China, but it may it may be similar to the thing that Floyd Sweet was doing as well. There's a lot of small similarities between one of these mechanisms and another, and for some reason a lot of these have to do with null field magnetics, where what you're looking at shouldn't produce a field at all, but in fact it does. So, because I mean, even on this thing, you've got two coils bucking each other, right? So, I'm at a loss to put any intelligent explanation as to why this thing would work. But what I can say is that what it is very similar to probably a good half a dozen other people in concept, because there's a cancellation of a field in a magnetic system where in close space there's a field, in far space there's no field. Maybe we'll figure out what that means. I don't know. Right now, that has a resonant frequency. We know what that is. It's 3 1/4 megahertz.
Can we wire a different way that I found?
You can do anything you want.
Cool.
Yeah.
It's
What do you want to do?
I want to do base of this one to tip of that one,
Go ahead.
and then
Yeah, right.
base of this one to tip of that one.
Go for it.
And then
Do you want the soldering iron,
I think
or do you want to do it with copper wire twist?
I think just twisting it.
Here, and some.
Base of this one,
Want
and then
here, you want some of this, and some of that.
Franklin, what needs to happen
Here, there's pliers there too.
per your understanding to get these things to start accumulating energy?
the only thing I found is the rate of change. If you could go beyond the classical limit of linear things, the only person that I've read about that did that was this Japanese scientist in Japan called Hideo Samu, and he's looking for a third differential when you pulse something, and if you see a third differential, that's that field that'll agitate the environment and then it'll suck it back in.
You're saying there's a third, like an echo.
Yeah, but there's a first differential linear, second differential, third differential, and he's seen that in his experiments. So
Okay.
your explanation makes sense, because if we could have a third differential effect on this, we'll be able to agitate and pull that extra field inside. He said it's a positive EMF when he looks at it in his system, and it bucks back into the system in a way that he's able to capture it and move it around.
See, that's what was curious about Floyd Sweet's work, is that Sweet.
He was getting DC pulses out of his coil.
Yeah. As far as I can tell, yeah. And I thought, okay, that's kind of cool.
Yeah.
Yeah, that's cool. And there was another guy named Hubbard years ago in Seattle, who had powered a boat on the bloody thing. And that was not a trivial thing to do, and I'm not sure if it was real or not, but it appears to have happened. Let's see, I need a support for this.
So Franklin, what needs to happen?
Let's
Last
see.
time you got this working, right?
Supports.
Well, I didn't know what was
There is
happening when
my
it was happening,
support.
and I was looking for just any kind of
Reaction.
reaction at it, and
Dun-dun-dun-dun-dun.
the way we had wired it was base to tip, which keeps everything in series. Don't know if that's gonna. doesn't seem a proper way to doing it because you keep things in a almost in an infinity loop between the two coils, and somehow that nature working in infinity, passing the energy around in an infinity way seems to be the way nature works most of the times.
So did you see the circuit that Daniel was using for the coil, J. Kirkwood?
Which one?
For
this?
Yeah.
Yeah, that's the one I simulated.
Okay.
That was the same one.
Okay, yeah. So
Yeah.
we just had a transistor and a potentiometer that was...
Right. Transistor and a variable resistor for the base.
So what you setting up there?
I'm just going to measure the inductance of the coil.
All right.
Let's see if it's even remotely close to what I thought.
It's tricky how you do that.
Okay. This is a bridge. This is a, let's see what we got here. Say an inductance, capacitance, resistance bridge. This is interesting. When I was playing around with the, when I was looking at the photographs of these things, one that was built approximately like this, I estimated on the computer about 10 millihenries. Right? That was that simulation we just looked at.
Is that what you're getting?
I'm getting 11.38.
That's pretty cool.
Yeah. Yeah, that's it. Okay.
How did you do that?
Well, it works like this.
The motor turning into capacitance at some points.
What, the gray motor?
No,
No.
Gabriel Cron,
Don't know that one.
which turns out to be Floyd Sweet's mentor,
Oh, okay.
because he worked for GE as like the top research facilities that GE had.
Okay.
Anyways, he was introducing tensors into electrical engineering back in the days.
Yeah. So what's your new setup here, Frankie?
This is a series setup.
Yeah. Base to tip, base to tip.
The frequency on that is 1.6 megahertz. It was about half the frequency.
Yeah.
Half the frequency.
So it's a very spiky signal you got there.
Hold on.
Doesn't change so much when you put...
Oh, should we solder that?
Yeah, I don't think they're making a good connection, so I'm gonna solder that so that we can.
Did you have your like
I've been designing inductors all my life. You know,
So-
you look at a picture and go,
Oh, I see.
Yeah, about 10
Yeah,
milliamps.
yeah,
Yeah.
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 Got it.
Yeah. It's just, you do this so many times, you just get a feel for it.
Alright.
It's okay, now.
So what is the inductance in layman's terms? It's not
Induct-
conductance.
No, it's a reactive term like capacitance. And it's, instead of the energy being stored in charge, the energy is being stored in a magnetic field. And so instead of electric field, you get a magnetic field. And in the magnetic field, you have a okay. Now, yeah, see, now you got something significantly better. We weren't getting much at all before. Oh, dude. You can't push the duty cycle on it too much. Okay, so right there, what did I say? It's about 1.6? Yeah. 1.6 megahertz.
Okie doke.
That's on. Now, if we do this, and talk to it nice.
I think it's just the connection.
There we go.
No, it's not.
Well, no, the frequency will shift when you add the probe because of there's about 7 pf on the probe. And that shifted us down. What did I say it was before? 1.6. Now it's down to about 1.16 megahertz. And yeah, so that's the second harmonic right there of the driver. Yes, it is. Okay. Right there, we're getting, once again, we're getting about 800 volts. 800 volts peak to peak.
So is that quite normal when you put in low volts and you get out high volts because you're putting it through a coil?
Right. When you're in a resonant system, it's a bit like taking a bell and tapping a bell. The amount of energy that's used in the tap is not all that much, but it spreads itself out over the resonant energy of the bell.
Okay.
And all of this, all resonant systems are no different than a bell. And you also notice that, you know, if you take those Tibetan bowls and you take the wood stick and you go around these things, you'll notice if you go too fast, the bouncing of the edge and the edge of the handle, if you hit it out of phase, it kills the tone completely, right? But as soon as you get it just perfectly in phase, where it's just touching at each resonant note peak, that you can build it up and build it up and build it up. And then you'll notice again, as it builds up very, very loud, if you're not careful, it'll kill itself very quickly because of it's out of phase. So the same thing is Same thing as this. This is no more than a bell tap. Whatever. So you get about 800 volts out of it, peak to peak. That's not too bad.
Would the Q drop though?
No, it's still about the same.
Same Q.
Yeah, which is sort of odd because in this case you've got the coils in series, right? In the other case you've got coils opposing. You still get about the same voltage.
So in this one, even though they're in series, their field are still opposing.
Let me take a look. No.
Okay.
No, because I've got, if you call this plus, right, then minus is going over here to this plus, right? So the other way that we could do this is to hook the centers together and drive one in, right? Can I do that?
True.
Let's see
Oh,
what
yeah,
let's see what happens when we do that.
Yep.
Okay, we'll separate those. Nanosecond pulses, and then he would just phase adjust those things into the coil. You get absolutely
Total.
one direction energy transfer into those coils. Okay, so now we know what this is. Did we want to excite this thing?
Yes, please.
Shall we excite it?
Let's get it exciting. Yeah, if we could try and compare it to a normal load, like we were talking about.
A normal what?
A normal load. I mean, like a normal circuit, if
Right,
you will.
and that box over there is a normal resistive dissipative load.
Okay, great.
Right.
So that we have some sort of comparison, right?
Right.
Exactly.
I mean, LEDs are LEDs, but a real resistor is something to admire.
Okay, great. So, yeah, if we can just recreate what Daniel's doing on his videos, that same circuit, and where he's claiming to be getting more watts out than what he gets in. Well, that's
Okay.
what he's showing volt and amp going in, volt and amps coming out, and adding them together, or timesing them together, and getting his watts. So what we're hoping for is to get a more comprehensive analysis on that experiment, and see if indeed we're correct,
Let's go find
or if something else is happening and we're just not able to understand it.
I need 100K ohm pot to duplicate what he was doing, right?
So do you think you're gonna, I mean, with the Utron, what are the next stages of development?
I have ordered and they're still coming. I'm going to put a wire on the base of this all the way around, and I want to quarter match it to this, or if anything, halfway match it. And then I'm still not sure if I need to make it a pivotal coil that can go this way or this way just for tuning. And I think if people have like a way of tuning it without doing anything, that might be easier than trying to like change capacitors and inductors. So I'll do that. I have a primary capacitance I bought and a big heavy secondary one. So it's just a matter of putting the capacitance on it to get it to just. What my thing is third order effect. When he mentioned through the environment, you could agitate the environment, and the environment just puts it back in. And Hideo Sama is the only one I've read, and I've talked to, and I've met, and I sent him a pair of my coils, and he says it finally has his system self-resonating, but it doesn't work with the coil separating. And they're based on the same geometry.
Well, big congratulations.
So following on his footstep, I'll try to do the same thing here with what this one's doing, and
Well, huge congratulations for getting so far, bro.
yeah, and I'll show you what he's saying.
Okay, cool.
I'm hoping I can meet him again at the conference next year.
Okay, cool. Tesla Tech Conference.
No, space propulsion.
Okay, yeah. You were designing some of the systems for a competition where...
No, that's a different one.
Okay, okay.
Yeah. No, this one's
Apparently this way is up. And it matters which one is on the outside and which is on the inside.
Okay.
Do you want me to get the details about that?
Yeah, it might be handy.
Okay, okay.
Voltage transistor on it now. Okay, so collector goes to dot and base goes to not dot. And these are both going in the same direction, So it's going to dot and base goes to not dot.
So have you had looks at these kinds of things before?
What's that?
These rolling coils.
Yeah, look at them.
Have you put them on your bench like this before?
No, I mean, honestly, the one that I was going to goof around with was the Floyd Sweet stuff.
Who's he? I don't know.
Floyd Sweet?
Yeah.
Franklin can tell you about him. He's another curious individual who... Okay, so this is not dot. And we bring that down to here. Okay. Right. And then that's it. Where's that wire?
Oh, on the floor? The white one?
No, the top. Oh, here it is, right here.
Oh.
With the snakes out, I'd be bit. You know, it's a funny thing about expectations. If you have too many of them, you'll be disappointed.
Yeah.
So I try to limit my expectations to simply the observed.
Yep.
There's a power supply down there. There it is.
There it is.
God, what a mess! What a bloody mess!
Oh my gosh.
Right.
Wow.
Okay.
This is fun. This is like the bell ringer's paradise.
This is... Okay, it's not there.
Wow. Did you collect them or are they all like functional?
No, they're all functional, yeah.
Oh, cool.
Wow.
It's just that I had to move out of one place and into another in short order, so everything just got heaved in here, which is sort of tragic. I've got to get all this all sorted out. There they are.
So let's hope this works, and then we can. Let's hope this works. Then we can get some funding, set up a facility, and we can put it all out.
Well, wouldn't that be good? Yes.
That'd be great.
It'd be just
Oh,
lovely.
come on, the optimists! Come on, the free energy.
Well, you know, it's not that it's impossible. It's that it's unlikely in classical thinking.
Yes.
That's all.
Oh.
So,
Yeah.
and I, quite frankly, I the only reason that you, me, and Molly McGee are all together today is because all of us have the same conviction that this is a more than just a possibility. It's a probability. It seems as though history would say that too. Mm-hmm. So we can go this way.
That's far up.
Lunacy. Total lunacy. I
These are moon plants, aren't they? Aren't those called moon plants?
Those are the daturas.
Okay.
And then over there on the fence, something you really enjoy are, you see all this little green fruit?
Yeah.
Those are passion fruit.
Oh, it's a real
They're
passion.
absolutely amazing.
No.
They have to be red and wrinkly before you can eat them.
Oh my God, those are going to be good.
And they're intermingled with all the grapes, right?
No, passion fruit and grape.
Passion fruit and grapes. As a matter of fact, I think in here.
It's just avocado now.
That's the avocado. That's our first avocado.
Yeah.
That's our first avocado ever. And then, wait a minute, where is it? I saw it earlier today.
What did you see?
And I thought this would be a good thing to note. We just had a tree taken out here that had was about ready to bust the fence open. Somewhere in here,
A bunch of grapes.
there's actually a bunch of grapes left that we. Oh, look. There's one. One came. No, there's two. There's another one in there. They just drop.
See, this is the over unity technology. You get one seed, it accumulates the energy from the environment around it,
Yep.
organizes it harmonically, grows into a big plant by doing so, and then produces lots of fruits with many seeds.
Lots of fruit.
And they all have many seeds.
Oh, bloody hell. You know, and I meant to make a mental note. Ah, here they are right there. Speaking of mental notes.
Look at that.
Here, try these.
Okay, all
These are Grenache.
Sure. Thank you so much. They're beautiful.
Yeah.
Sublime.
You've got the last of the grapes.
Last of the summer wine.
These, however, are absolutely amazing.
Wow. Thank you.
Thank you.
So could you tell us again what this power supply is?
Well, this is just a power supply to run the oscillator. And this is able to put out 1.5 amps at up to 50 volts. And the reason that I'm putting this capacitor on here is that since this is what's called a blocking oscillator, oftentimes the recoil energy from a blocking oscillator will go back into the electronic power supply and bugger it. So I'm putting a decoupling capacitor on it so that I can keep the energy flow local to this capacitor instead of going inside the power supply. Details of living.
So what's some fun projects that you've been involved with other than this?
I'm modifying Joe Satriani's guitar amplifier to become something other than what he originally had. And that's always fun.
That's great. Have you seen the potential of these used as 3D speakers?
What's that?
Have you seen these used as 3D speakers?
Who?
These coils.
I'm sorry,
Have you
what?
seen them being used as 3D speakers?
No, I haven't.
It's
No.
good fun. Stick a big magnet in the middle of them.
Oh, I see. And then
Put it on a metal dish or something.
drive it with an oscillator.
Yeah.
Okay.
So, if you're going to work on Coil Suite, where would you start? Since it seems like a big trick was getting the magnets to remember that oscillation.
Yeah, you've read it, right?
Mm-hmm.
Yeah, I don't buy that shit.
So it's just to
I really
detract people from.
Well, it may be. You know, if you, I mean, think about it for a minute. Realistically, to take a magnet and say, okay, well, I'm gonna impress 60 cycles on a magnet, right?
Mm-hmm.
and then get that to remember that it was 60 cycles, so that when I start feeding energy from itself back into itself, it will synchronize to that frequency, right?
Mm-hmm.
Try to figure out the physics of that.
Yeah, I couldn't. I looked at it. And
Yeah. Right now, if and what he does is he does a conditioning.
Mm-hmm.
And so what he does is he takes a magnet. In the center, he reverse polarizes and weakens down to a couple of hundred Gauss or so,
Okay.
while everything around it is at 1,000 Gauss. And that right there is a curious thing, because now he's got this area where the domains of the magnet are able to be easily manipulated by an external field, where the other ones have a high retentivity. Right? So, you know, so what the hell does that mean? And it means that the domains can do things in ways that the permanently polarized domains can't. They can move around.
Yeah. So emotional
Right.
field.
Yeah, so you get emotional field. Not emotional, but emotional.
Well, we would
Okay.
have free energy if we could tap to how much emotion there is around the world.
Yeah. Right now. Okay, so now we have that circuit. We're going to double check it. Minus goes to the emitter. Yes, it does. Verify it. That is the emitter. That is the emitter. Base, base. Base is going to a resistor. Resistor goes up to the not dot. The collector goes to the dot. And both of them hook to plus. And the resistor right now is set to 100 k ohms. And going counterclockwise reduces that resistance. The transistor is a 2N5328, which is a 6-7 amp 150 volt transistor, a little higher voltage. Let's see, now what do we want to look at this with? We have to put a load on it. Okay.
Yeah.
Did you have a load?
He was working
Or did you have something you were slapping together?
No, that's just crap. Don't look at that.
This looks.
You don't want to go near that. That's horrible.
Let's see. This is horrible. Oh, it's bloody horrible. Do you think you got all the cathodes lined up in the right direction?
No. I've got two lines of them lined up in the right direction.
Got it.
Otherwise, I was hoping that you might have a load. Can't we?
We're going to use the
resistor.
resistor, yeah. That's exactly what we're going to do.
You don't have any LED boards, but I mean, so okay. Never mind. Let's use resistor. Okay, no, it's okay. Sorry to bang it out like that. I just meant. I don't really know. My experience in electrical engineering, what electrical engineers may likely have or not, is
The likelihood
just
of
guesswork.
having a bank of LEDs laying around is fairly, well, yeah.
Okay. Well, I could have built a bigger one, but
But then?
what Daniel's doing with 1 watt and 500 LEDs, I mean, should that classically be possible?
Like I said, you know, when you look at the simulation model, LEDs do a very peculiar thing when you hit them at 10 times the normal operating current at a low duty cycle. They look very bright. And in fact, they are very bright. They're brighter than they are when you run them DC at a lower current, or the normal operating current. So even though the total amount of power that goes into the LED might be the same when you average out the duty cycle or a DC condition, the light output from a pulsed LED is actually brighter than it is for a DC LED.
And being able to light many more?
Well, that's just the reaction of this coil. This is an induction coil. And so that's why it was curious, this whole circuit here, because this is a if I were doing this, I would do a single turn, right, to drive the base. I wouldn't drive the base from a coil of the same length, because it would tend to be lossy. But that's just engineering, right? So I'm going to take this down, put that up, put the current limit up.
So these types of coils are used classically to produce high voltage?
Any coil. Any coil that's a blocking oscillator was, and in fact, in that oscilloscope right there, the oscillator that drives the high voltage in that oscilloscope is a blocking oscillator. And then it has a limiter built into it to keep the cathode current, stabilized. So blocking, and I've got a number of really old pulse generators in there that use blocking oscillators for the timing circuit, right? And it's what some people call a relaxation oscillator. When it uses magnetics or classic electrical engineering, it's a blocking oscillator. It's a positive feedback oscillator. And it goes to a saturation, then it collapses, and then when it collapses, it goes to the other direction. Then when it goes the other direction, it shuts everything off, and then it starts to turn back on again, and it regenerates to a very high conductance. Then it saturates, and it goes back down again. Right? It's this period. You can see it in the simulation. I don't know what this is going to do, but we'll find out in a second. So I want to make sure that the scope is hooked up so that we can see who's on first, what's on second. And what I'm doing here is just threading. Do I want to do that? Just hook the bloody scope probe up to the resistor and to the output. The output is the collector of the transistor. So that's what we'll do. We'll go directly, same as it ever was. Go directly to the collector. Do not pass go. That's right here.
What do you think? You think it's gonna do something out of the ordinary?
I don't know. I do like the way the magnetic field would just revolve like this on one winding, maybe like this on the other winding. Combining both would be interesting to see.
Okay. One wire. Okay, that's the collector of the transistor. And the emitter of the transistor, which is right here. amazing. Okay, and then we'll hook this. That's the emitter. This is the collector. So across this we should see something raucous going on at some point. Okay, let's see what we got going on. I'll put that in current and then drive it up. Oh. We will put on here about 100 k ohms. 100 k ohms. What do you think? 100 k ohms, 10 k ohms? Well, how many LEDs did he have on there?
He had 500.
What was the color of the LED?
480 white ones.
What was the color of the LED?
They were clear white.
No. What was the color of the light?
Oh, white.
Oh, they were white LEDs.
Yeah.
Okay, so that's about 3.5 volts times how many?
There was 580 done in little batches of about 36. 36 in series, and then in parallel another 36.
Okay, so it's 36. So the total stack height was 36.
I think so.
Yeah, okay, so it's 36 times
7.
36. 36.
Oh, but he had a very different coil. His coils are like triple stacked like that, and then wound with a 12 to 5 winding.
Okay, so
There's a lot more. There's a lot more.
well, that's 118 volts.
Okay.
That's what that would come out to.
Okay. Well, I think we should expect about 300 or something for this.
Well, if he had a 3055 transistor,
Yeah.
it would destroy it at 300 volts.
Sorry, no, I meant 300 LEDs.
300 LEDs, but the total what's
Hey, Daniel's here. He's here.
oh good.
Hey, Daniel. How you doing? I'm here with Kirkwood and Franklin. How you doing, bro?
Hello, Kirkwood and Franklin.
How you doing?
Hey, Daniel.
How are you, gentlemen?
Good.
Hey, I don't suppose you'd be able to jump on Skype, would you, please?
I could, just give me a few minutes to make it out to the
Hey, bugger's oscillating.
Okay, cool. We just got the coil
I'll
on.
be right on.
Could we ask you a quick question, so long?
Yeah, for sure.
Okay, how big was the load that you put on, or do you think we should put on for this small coil?
That's pretty cool. It actually
Well,
oscillates.
what you can do to really oscillate it is, get a couple of neons in series. Maybe like 10 of them in series and try to oscillate them at different frequencies.
No, it's oscillating right now with a dummy load
We've got it with a dummy load, a big
of 100 k ohms.
a big resistor of 100 k ohms.
Okay, yeah.
And that's
So
how many
if
volts is
that
that?
works,
That's 20. That's okay. So
Hey,
that's
I've never
20.
tried oscillating it with a resistor, but
There's 50.
with some neons, I've done that for sure, and that works. And also,
Okay,
long
now
load
let's
of
go
LEDs works too.
from
Okay.
there.
Well, if you could jump on Skype,
Signal
I'll put the
out.
video on and see the setup. It's amazing what he's got
Set
here.
out.
For sure. I'm running out now.
Okay, beautiful. Thanks, bro.
There you go.
All right.
Cheers.
Okay, so now let's get this guy over here. There's 10K. ohms.
Still down low.
Still not much. Okay. That's pretty cool, actually.
There's something.
Still 25.
What's the current?
0.
0. Very minor.
So what you doing now, Kirkwood?
Okay, so that's the waveform coming out of it. That's 20 volts per division, so we're at about 20 volts RMS, right? Into Aha, there's a critical point. Now I'm lowering the base resistance.
You should hear the coil start singing. It goes like.
No, it's at 12 kilohertz. That would be a very high pitch.
Oh. Well, this is not a 12 kilohertz. No, it is. No, it's like super squeaky. It's like.
I think if we put something in the middle, it might.
It squeaks even without it.
Really?
Yeah.
This is very interesting. Okay, so now, well, you will hear you'll hear magnetostriction. Yeah, you'll hear magnetic. You can. My ears don't hear that anymore. My ears used to be able to hear that, but not anymore. So now we're 11 and a half kilohertz, right? Well, this is getting interesting. So, don't know what it's doing, but we're going to find out. Ground reference at the bottom. There. So now you're looking at the voltage across the transistor. So we're feeding in 25 volts. And we're getting about 100 volts peak out of it right now into 3,000 ohms. There's 2,000 ohms.
This went up a little bit.
Yeah, there's 1,000 ohms. Okay.
Let's see.
So now there's 1,000 ohms.
4, 5, about 50 milliamps.
And I'm adjusting the base resistance.
It's going
So
to
that
75 about milliamps. 100 milliamps.
wow. This is pretty interesting.
125.
So now it's at a frequency that you could say is, you know, at that high pitch singing. No, it's at 6 kilohertz.
150 milliamps.
Yeah. Okay. Now I need to get the wazoo meter. Here it is. This is a clip-on ammeter. So we can actually monitor the current going into the unit.
This thing is singing.
It is singing, yes.
Oh.
Can you hear it?
Yeah.
The camera will be able to. Can you hear it?
Yeah.
Maybe my ears are shot.
That's it. Too much rock and roll.
Yeah.
Too much rock and roll.
Too much rock and roll. I can hear it well.
Too many loud concerts.
Well, listen to my music so loud, I'm happy I can hear it.
Let's get this guy on the road.
A little bit. Like,
Super high squeaky.
Okay.
Okay, George is online as well.
And now we're also going to put a current probe onto the resistor. Okay, there's that probe. This is a current probe.
Okay.
And it's an attendant amplifier. And we're going to now monitor that we're looking at the voltage across the unit.
This one here.
with video?
Yeah, absolutely.
Okay.
Hello, brother.
Hello.
How's it going, brother Daniel?
Doing good, doing good.
Good to have you here. Can you see what's going on?
I can. Hello. Is that Kirkwood there?
Yeah, that's Kirkwood.
Hello, Kirkwood. Nice to meet you. Hello, Franklin. Nice to see you.
Yeah, likewise. Here, maybe I could just... I'm gonna move you around so you can see.
Okay.
Thank you.
Can you see well?
Yes, I can. Looks beautiful. That's a nice big device there. Is that a signal generator on a scope?
No, that's the coil oscillating right now into a dummy load of, I think, 1 k ohm. Yeah. It's going into a 1,000 ohm dummy resistor.
Beautiful.
And it's pulsing at what looks like about 150, almost 200 volts peak. Out of a 25 volt power supply.
Beautiful.
And we have about 150 milliamps coming out of that. I have to insulate this thing. I forgot. Now I've got to demagnetize this thing.
Yeah, I've got to switch the battery on
Okay.
Beautiful. It's like it's like the baby's being checked by the doctor over there.
Yeah.
Or the doctors, rather.
Oh. I think I would qualify as a nurse, Daniel.
You get a nurse, Charles. That's okay. They're still very needed. Nice.
No.
So,
All right.
we got it lighting a CFL on our end over here.
Yeah, you would. You're right.
Pretty bright for. We're getting 38 watts. So we're running 38 watts and lighting all these panels over here, or flickering them at least. We need a better capacitor.
Okay, so we got 170 milliamps. 170 milliamps.
What's that going in?
That's going in 170 milliamps at 25 volts. Right? So, yeah, 170 milliamps at 25.17.
A little less than 5 watts.
No, yeah, 4¼ watts, right? And then we have, I wonder if I can get an average on that. This one.
It's super trippy having Daniel down. It's like head is at head height.
Modern technology. Be there real time.
Okay, so
That's
one,
it.
That's 20 milliamps. Okay, that's 20 milliamps. Into thousands. So right now, it's 0.4 watts. So it's 0.4 watts into the 1,000 ohm resistors.
So, how many was going in what?
0.4. It's 4 going in, 0.4 coming out.
Okay, so
0.1 in terms of. Let's see if this is.
0.4 going in, 0.4 coming out. So no change.
Well, no,
That sparked a little.
yeah, the sparkle's a little odd. That's my wrong lead.
The high voltage
Yeah,
lead.
that was on the high voltage lead. Want to do that? We on this one?
So Daniel, you said you haven't pulsed these things at high voltage, like kilovolts.
Well, no, not kilovolts. No, we went up into 600 volts. But that's pretty much the highest that we went in as the input.
Okay.
Is that what you guys are doing there? You're pulsing high voltage?
No, this is
Well, the voltage is going up to about 150 some odd volts. The current is going to 150 milliamps. Peak.
So the current is pretty much the same as the input, right? Maybe a little bit increased by like maybe 10 milliamps or so.
No, I mean the DC current going in is 150 milliamps.
Okay.
170 milliamps. Right.
170 going in
at
and
25
how much
volts.
comes out?
At 25 volts.
Okay.
Okay, so it's about 4¼ watts. What we have coming out is what we have coming out is a couple of hundred volts at 150 milliamps at a low duty cycle. And the frequency is about 5.3 kilohertz. What kind of frequency are you getting out of the coil?
I think that coil resonates at 13 kilohertz or so.
Well, it does when there's no load.
Okay.
Yeah, it does. It started at 13 kilohertz. Then as we kept adding load to it, frequency would go down, right?
Sure. So that's pretty much the same thing that we were finding, is that different loads will change the different resonant frequency, of course.
Yeah. And it takes a little more for the coil to come into a reaction. Now I'm going to turn the
So do you think that also it would then operate a little bit better at a higher voltage?
well, what I was saying before was that this circuit, where you have I think you were showing I don't know if it was you, but somebody was showing a 3055 transistor, right?
Yes.
And I'm using a higher voltage transistor because a 3055 is limited in a stock 3055 to 60 volts.
Yes.
And typically 100, and the H series was a 100 volt breakdown, right? So ideally what you want is you want a horizontal flyback transformer type transistor, which is like a 1200 volt transistor.
Okay.
To operate as a blocking oscillator, because this is a blocking oscillator, right? So the other thing that we were talking about before you came on was that doing the impedance match to the base is best achieved with a single turn instead of having the base drive coming from the same number of turns in equivalent cross section as the primary.
Okay.
Right? Because then the amount of power lost in going to the base is minimized. Right?
That's true. Okay.
Right.
Okay.
So I mean, I think there's 12 wires in this bundle, right?
Yes.
And so with 12 wires in the bundle, and the base of the transistor is less than a volt, right? This limiting resistor right here, if you can see it, is it's a 100K ohm resistor. I'm using a wire-wound pot because I wanted to be able to not destroy the pot when I turned it down.
Yes.
And so I've got a 5-watt potentiometer on here. Right.
Beautiful. Yeah, that's not in Radio Shack.
Nope. No, you're not going to find that one on Radio Shack.
If you could give me a site for that 5 watt that you have there, that would be great.
Maybe I'll dig one out and send it to you.
Oh, thank you very much.
But what we should be doing is taking a single turn. Instead of having 12 wires, have 13 wires, and have that one wire come out to drive the base.
I see.
So if we have time tonight, what I'm going to do is rethread this. I'm going to leave it the way it is, But
with another
I'm
wire.
going to follow one of the paths with a single wire, and then bring it back to the base. It'll accomplish two things. One, it'll allow the frequency to go up at a high load, right? And the amount of energy lost in driving the base will be reduced.
Beautiful.
So,
okay. That sounds exciting.
Did you see the waveforms over here?
No, I did not.
Okay,
It's a little. Okay, now it's
Well, by the way, you just did something interesting. Bring the computer back over. There. Okay.
It's capacitance.
Yeah, that's the capacitance loading. That's interesting.
But that's only metallic, right?
Ah, so that's that's the eddy current in the back side of this computer. All right, that's what that is. It's not electric. It's a magnetic field. In fact.
Yeah.
Okay, and the other thing I wanted to do before we went away here with this, this thing is neat.
Can we be clear?
This is not even warm. So what?
I don't quite understand.
What are we talking about?
Yeah. If you, as I understand, did you
very
read an
cool.
increased watt output?
There is no increased watt output at this point, right? But there's something else I want to do. I want to pull the magnet out.
Shouldn't there be an increased watt output at this point, given what we're supposed to be building?
This is identical to everything that you got, except that that's a resistor.
Okay.
Right.
So Daniel, are you getting that? Do you have any idea why that might be?
So yeah, we typically don't load it with resistors. We load it with a high number of LEDs. So now, what's the difference between loading it with a resistor and loading it with LEDs, or let's say a strand of neons? What does it do differently to the coil?
Well, neons are very hard to categorize in terms of dissipation, because a neon discharge is a plasma discharge that at low frequencies begins to turn into an arc.
Yes.
Right?
Yes.
Because the
And it
electric
turns purple.
it starts turning into an arc.
So what about
reason is
300 LEDs?
the ion transit time from cathode to cathode is, or from element to element in a neon is rather short. So less than a half a megahertz, you start getting transient arcing conditions in the plasma. So
Sure.
it's sort of it's a complex load, because a neon discharge or a plasma discharge is also a negative resistance in its character.
So what about using a long strand of neon? It's like 300.
Well, that's what I'm saying. The plasma discharge is a
Excuse me, not neons, LEDs rather. My apologies. So if we're, like for instance, we're getting these increases, or we're getting so many LEDs to turn on using a very low voltage. So we're getting let's just 100 foot candles per LED. Is that
that's because of the flyback of the coil. As a blocking oscillator, the transistor goes into saturation. The volt-second support of the coil collapses, and the transistor turns back off again, right?
Okay.
So, because the coil recoils in the opposite direction. Then everything turns off, and then after a little settling time, it starts coming back on again, because the biasing resistor to the base begins turning on that transistor, right? So you get this cycle, this cyclic bang, 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 turning on the coil, turning off the coil. Every time it turns off, and it turns off rather rapidly,
it's a back EMF spike.
The
That's
back
pretty
EMF,
massive.
yeah.
Okay, so ideally then we want to use these in lighting units, and that means that these coils would then be effective for that.
Yeah, and in fact, if you go to Linear Technologies site, right, it's a company out here that builds semiconductor devices for power supplies. All of the LED string drives that come from a low voltage are done precisely that way. It's energy stored in the inductor, and the flyback then ignites or lights all of the LEDs in a string at a higher voltage than the source voltage, right?
Okay.
And then
So so do you think that at 1 watt of power it is feasible to get that many LEDs?
Oh yeah, yeah. And then what I was saying before is that in LEDs, when you look at an LED and look at the amount of light output, the number of lumens that comes out of an LED, curiously, is higher when you pulse them at the same power as you would run them at DC. So you can actually get more light out of them at lower power when you pulse them.
Okay.
It's a very
so then, effectively, what are we saving here by making these coils and implementing for these type of LED systems?
We don't know yet.
Okay.
We don't know. I've never seen one of these before today, so I don't know.
Okay.
You know. However, I was curious. I ran some simulation. I was looking at the web, and I was looking at the coils and so on, and the dimensions of them, and I estimated them to be somewhere in the vicinity of about 10 milliamps, right? When we measured this coil, it was 11 point what? 7? 11 point. So it was not much over 10 milliamps.
Okay.
So the dimensions and the expected value of the inductance is about what you would expect, which was good. So there's no mysteries there.
Nice.
Right, but you can see the waveform now. We're loading it at 300 ohms. Wow, that's cool. And we're getting 300.1 300 milliamps. 300 milliamps peak and a duty cycle of 0.2.
This is like 140 milliamps over here.
What is it?
Input 140.
140 milliamps?
Yeah.
Not
A
much.
little less than 1.
No. What,
Oh wait, 2 point.
No. We're on.
1, 2, 2.
It's a 1.5 amp limit, so we're at about 250, 300 milliamps.
Yeah. Sorry.
Yeah. We got 300 ohms here? 300 ohms.
Running low on power.
Go 0.2x.
Is it okay?
Okay, now. Wow, this is interesting. Let's see what this thing says. This has got to be more than that. It's 300 milliamps. That's 25 volts.
Mm-hmm.
Is that right?
Yep.
So that would be about 7.5 watts. And we're about maybe 5 watts out right now. So
We're matching the impedance.
we're starting to get closer to when we started out. You know, the energy it was about 1/10. Now we're at well, it looks like we're at 3/4 coming out.
And what have you changed?
Just
All I did is I changed the resistor value, the load resistor, and I'm playing around with the
Tuning.
adjusting to see what we can get out of it.
It's quite good when you've got LEDs because you can tune to see when they're bright. But,
Right. Well, here
it doesn't seem to
here we have this mystical stuff called oscilloscopes.
Okay.
And here's the frequency. I don't know if you can see that. It's 4.72 kilohertz. Right.
Okay.
You got that? And then, so now.
You know what I also do to increase the energy that's flowing out of it? We go ahead and we put a 0.15 UF capacitor across the junction.
Of
So
what?
we flow energy in opposite directions.
Which junction?
To smooth it out, alternating current-wise.
Which junction?
So basically you have a start finish of the wire and then another start and finish.
Right.
You're basically creating a series connection right to the middle, so the finish and the start. But right there you're going to plug in a capacitor in parallel.
Okay,
so you're
I'm going to
taking
hook
both
one
of
end of
those-
the capacitor to the collector of the transistor.
Yeah, so let me just show you.
Yeah.
See, so right there we have, you have your start, or your start and finish going into the amplifier. See, so that's where that wire is running. And then these are the other leads, and they're going right there onto a capacitor. And now that capacitor, when it collapses, it's lighting all these lights.
Yeah, right.
Yeah, so we're getting that at 38 watts, of course. And really, that's just, we're really just using 18 watts for all these lights, rather than the full 38, because 20 of those watts goes just to turn on the amp.
So the capacitor is going to go from the supply line to the collector?
Through the coil. So through the coil, from the supply line through the coil in both directions, and where you have that output, then you connect the capacitor in parallel to the output leads.
Okay, so one end of the capacitor is connected to the collector of the transistor, right?
No. Right now we're talking alternating current. So it's a slightly different setup. Not using that SEC transistor, but using the sound frequency direct oscillation from the signal generator through the amplifier, and then into the coil.
Well, what kind of amplifier are you using?
So right now we're using, I'm not sure what the specs are. It's an Insignia. It's a standard type, home stereo amplifier.
Oh, okay, so it's an audio power amp.
Yeah, audio.
Okay.
So,
Okay, so it's not a self-excited thing.
No.
Okay.
So that's basically what I was saying. So when we do that over unity measurement, where we have all of the meters on there, we typically use that 0.15 UF capacitor across the output leads, and then into loads.
Yeah, okay. So you're tuning it with that cap.
Yes.
Yeah.
So it's like a buffer. It's a Tesla. It's a Tesla cap.
Yeah. Yeah. It's a resonant cap. God, you got a bunch of those things back there, don't you?
Yeah. It's
Now I was looking at the coils up on the wall.
This is a 14. These are both 14 watt grow light panels. These are both 3 watt regular LED, and this one is a 14 watt CFL.
Designed for what voltage?
So they're all operating designed for 120.
Okay, got it. And then your what's the input voltage from the amplifier?
Input voltage should be
going from the amplifier into the coil.
Yeah, let me just double check that. I think it should be around 50.
And the frequency?
Frequency we're running is actually a harmonic. It's 864
hertz.
Yeah, the capacitor brings it right back down. So that's can you see the voltage there?
Yep, sure can. Yeah.
52.7 going in.
That's AC
and,
at 800 and something hertz.
800 and something hertz. Yeah.
All right.
And let me just read the capacitor or the voltage off the output leads rather. So you see it's at 4 volts. So it's reading it somewhere around 4, and that's after you discharge all of that voltage into all these lights. So after I turn it off, yeah, let me try not to.
I'm lost.
Yeah, let's go and plug into the regular line here.
Yeah.
Okay. So now that it's not plugged in anymore,
Yeah, I can read it.
So we're reading 67 volts on the output.
Oh, with everything disconnected.
Yeah, with everything. Well, it's not actually disconnected. It's just turned off. So
Yeah, turned off. Okay. Yeah.
let's go ahead and disconnect it. So it's 67. So as I tune that frequency, we can get it to go up.
Mm-hmm.
So I'm just lowering the frequency, and you see that it's climbing up a little. And it
Right.
goes back down.
Right.
So 69, 70, and somewhere around 432, I think it starts to resonate with a couple of 100 volts.
Okay.
So that's basically the setup that we're running here.
It was very different. You know, we can drive this thing with a power amplifier. We've got some 200 watt amps in there with oscillators attached to them. So you're running a sine wave, right?
200.
You're running a sine wave, right?
Yes.
Okay.
So 246.
Yeah, I can hear it. Yeah.
So that frequency is 694.
694.
Hertz.
Oh,
yeah.
that's the voltage I'm looking at.
Yeah, that's just the voltage right there.
Okay. There you go. The boys in the basement. All right. So, do we want to run a self-excitation, or do we want to pursue the sine wave drive?
What do you think will be the most likely to try and demonstrate or explore what we're calling over-unity effects?
That's pretty much the sine wave that we use to demonstrate those over unities. Any video that I put up with the over unity meter has been with matching the input versus output amperage. That's been with sine wave input.
Okay.
Those little SEC circuits are just to make like off-grid applications.
Right. Right. So, okay. So just reiterate your audio power source is feeding one coil, right?
No, it's feeding both coils simultaneously.
Okay.
So it's not inducing from one to the other.
Okay.
It's feeding through both simultaneously.
Okay.
And then the outputs are going directly into the capacitor. And then from the capacitor, we're using that to run the loads.
Okay. So if I'm feeding this coil from an audio generator, are you feeding it with a stereo output or a single ended?
That should be stereo.
So you have a differential sine wave voltage, right?
Differential? I'm not sure what that means per se.
In other words, the output of the amplifier is the coil that's being driven by the amplifier. The output of the amp is driving one wire, and the other wire is going either to a ground return or the other amp, right? Right.
Not too certain, but I'll draw the setup for you.
Okay, that's helpful.
Okay.
Because we've got some 200 watt power amps here with oscillators built into them.
Alright, so here we have the sine wave, and this is the amp.
Okay, so which one is which one's the hot lead on the amplifier?
So this one would be the red.
Right.
And really, it works in both directions, so that really doesn't
right, but
doesn't
it's just a single channel amplifier, right?
Yeah.
Okay.
So now we're just gonna go like this, and this is gonna represent.
Okay. And put a dot on the start and the finish. or a dot on the starts.
So this is the start.
Okay.
And this is the start.
Okay.
That side. So what we're going to do is we're going to run this into here.
Okay.
And we're going to run this one over here.
Okay.
And right here we have this cap
Right.
connected right across the outputs, and that's a 0.15 UF, and that's that one right there.
Yep.
And it's a 2,000 volt cap.
Yeah. Yeah, I've got those.
Okay.
Here.
So
Let me
that's
just take a photograph of this real quick. Go back out from there. Okay.
Yeah, let me just try to hold it. There you go.
Got it. Okay.
Cool.
All right.
All right. Thank you. Very
Thank
good.
you.
Yeah, we can duplicate that.
You have to test out the baby over there.
Yeah, we are. We're gonna test out every which way from Sunday.
That's right.
Okay.
You know what? And as a matter of fact, I can go ahead. You know what? Since we're actually running the same, pretty much the same coil that you have over there,
Okay.
so we should be able to match exactly what it is that you're doing, except for the fact that you have different loads than we do.
Right. So we're gonna try it with a resistive load, and then we're gonna try a couple of other things while we're at it. So we'll see what we can see, how much damage we can do here.
Apparently, I can.
Yeah, well, you guys have fun then on your end, and yeah, it sounds like it's gonna be exciting. How long are you guys gonna be testing for?
Till everybody says I've had enough of this crap.
That's gonna be a while.
I hope so. Yeah.
Wait till the
Should we
Harmonics
give you a
are
call
going.
when we're ready again?
Yeah. Can we give you a call when we're back up and running on it?
For sure. Sounds good, guys.
All right.
Alright,
Talk to
cheers.
you soon.
Talk to you
See in a
soon.
little bit.
Thank you.
All right. Bye bye.
Well, the model is behaving like the model shows.
It's actually doing what the model said it would do.
Yeah.
Yeah. It's a very, very interesting bunch of stuff. Here, just right there. Just right there. That's a box of Tesla. It's a box of Tesla records. Oh yeah. Yeah, I have over the years collected just about everything he's ever written.
Ooh.
And I have all the patent wrappers and all of that stuff. Oh, there is that damn. I was looking for that. Crap. All right, now we got to get this bugger out of here.
Okay.
What these are is this is a very high-powered audio generator that has variable impedance taps on it, so that you can drive very high currents at low voltage or very high voltages at lower current. You know, about up to about 200 watts. Not the normal thing that you have in a garage.
So where did you get those?
What I was, yeah, gotta be careful with these things.
Oh, I thought it was longer.
No, it's not. Here, grab that.
Okay.
I used these when I built these very large 8-foot diameter Helmholtz coils for messing with the beam machines and testing the susceptibility to interference. Let's see what, here, lift it up. Okay, we're good. We're going to rearrange a few things. Here. There's our 0.15 capacitor. It's composite of a 0.1 and a 0.05.
Could we mic you up again, please? Is that alright?
That was interesting. Oh, there it is. Ta-da. Okay, now. Whoa! Shit! Okay. Whoa, shit. Okay, back down. Oh, that's you. I thought that was us. Heads up. Heads up. Heads up. Heads up. What happened? What happened? What did we do? Ooh.
Is this another one of those?
No, this thing went way over voltage. It went through the roof.
Oh, this is.
Hmm?
No, I thought this was the same one.
Wow. Well, this one is never going to see another voltage slide. We just killed it.
Oh, no.
Yeah.
On this charger.
This is the kilovolt?
Yeah.
That's the one.
Can't get fixed.
Huh?
Can't fix it.
Dude, we have now toasted. I wasn't paying attention, which was unfortunate.
Was that a very sensitive one where we needed the processes?
It's called eating the meter. Wasn't paying attention. So that's through the roof. So resonance is a very snaky thing.
That she is.
That she is. Resonance can bite your ass. Okay, now let's go back to this. Oh, there she goes.
200, 400.
That's 400 volts. Yeah, I did that to 150 volt meter. Okay. Pink. Okay.
It's a big spike over there.
This is the. Oh, can you see it? Good.
Yeah, I could see it as you narrowed into the resonant point.
Yeah, that's,
Yeah.
That's getting toward resonance.
What's the what are you looking at on what's the rating there? Is it 10 volts? 10 volt scale?
What is it right now? Oh no, I'm just that signature that you see there. That's just the scope probe hanging out next to the coil.
Wow.
And then I'm looking at the peak voltage over here on a meter, which is almost 300 volts. No, it is 300 volts. And that's into a 4,000 ohm resistor. I'm going to start dialing it down. In fact, what I'm going to do is go to a 1K ohm resistor. And try to tune the resonance. So that's a frequency of 1.98 kilohertz.
And that's the most resonant.
The meter up
that
here
you're
is
getting there.
Huh?
That's your most resonant point that you're getting there.
The peak of the resonance into a 900 ohm. No. What am I going into? No. What is this? This is 1K.
That's a variable resistor that you got there?
Yeah, it's a 200 watt resistor that can be varied from 1 ohm to 1 megohm.
Wow. So that just is for like design purposes?
Well, it's a test resistor.
Cool.
It's a load that allows me to, you know, get 100 watts of dissipation at any value. 200. Is this 100?
That's cool.
Yeah, this is a badass little resistor. This is
Nice.
this is the biggest decade box you're ever gonna find.
Oh my goodness.
Okay, so now, well, this is interesting. Okay, now my resonance is up over. I'm moving a lot of power here, so I'm putting. The hell am I doing? We need a different meter again.
Meter?
No, the voltmeter, the electrostatic voltmeter that says 200 volts. The one that the 150 volt one is gone forever now. Yeah.
This one?
Damn. Is that 200?
Yeah.
Yep, that's the one we want. Okay, now I'm going to turn this down. And go back up again. The voltmeter that we're using is an electrostatic voltmeter. So it's a set of Kelvin plates that drive a. You want to see this?
Sure.
Yeah. Can you see that?
Yeah, it's just like an analog.
Yeah, it's a regular analog meter, but it's an electrostatic meter. So we can. It presents no resistive load to whatever the heck you hook it up to. It only presents a capacitive load. And as a result, what is the capacitance on this one? The full-scale capacitance on this is, at 200 volts, it's 220 picofarads. Right? And that's 220 picofarads across a 1 k ohm load. So now we can read the voltage directly, the integral voltage.
Okay.
Yeah. And I'm trying to. Okay, so where's resonance? Okay, so there's. It's right through there. That's at 1.8 kilohertz. 160, 175 volts. 175 volts. Okay, and I'm at 125. Now you said you were at 50 volt input?
52 right
Okay.
now.
All right,
52.8.
I can set this wherever we need to set it, right? So
Beautiful.
I set the voltage at 50. Okay, now the resonance is up over 2.1. So I'll back it down, change scales, go back down in here, and come back up. Huh? Okay, there's 50 volts. And where's resonance? Ooh. Okay, so at I'm going home. The problem with this generator is the scale goes up to 2 and then it goes from 2 to 20. Okay, so there's 50, there's 55 volts.
It's a bit colder up here though.
Huh?
It's a bit chilly up here than down
Yeah,
there.
up and down in LA.
Yeah.
Oh, wait.
Come on, you're from London, right? Give it a break.
Just getting used to it.
You're getting California spoiled.
What's the temperature out there?
Oh, it's probably around, right now it's probably around 58, 60.
You have the same weather as New York.
Yeah. Lovely. Except they have to deal with New Yorkers and we don't.
Yeah, that's true. Beautiful people, no?
No. No.
Oh, come
All right,
on.
so yeah, we're at 1.78 kilohertz. This is with a 1 k ohm load, and we're at 92 volts. So we have 52 volts in, 92 volts out. 92 volts at 1 k ohm is going to be what? 92 volts.
1K? Oh.
You know, it's going to be like 0.9 something.
0.098?
Huh?
1000 divided by 1.
Yeah, about 90. Yeah, what? 95 milliamps or so.
Yeah.
Is that right?
Yeah, exactly.
Okay, so we got 92. 92
Divided
squared. Divide. So that's 8.46 watts, and then what we have going in is 52 volts at, what is this? So we have 52, and 180 milliamps. So we had 9.36 watts in, 8.46 out. I'm going to try and optimize the load. See if we can get a let's see, where am I? Where am I? Okay, there now I'm at 900 volts, 900 ohms. 450. Now we're getting back up to the 2 kilohertz range. Yep, peaks at is 80, 86, and we're 900 ohms, 800 ohms,
I think over there.
700 ohms.
Yeah.
So 1.6. So 70 volts and 700 ohms. So 100 milliamps at 70 volts. 7 watts.
Mm-hmm.
And we are at 52 volts and 52 and 0.15.
7.8.
So now we're 7.8 watts in, 7 watts out into our resistive load. Okay. So what I'm trying to do is find where the best load and power transfer is. It seems like we're getting better as we go lower, isn't it?
Yeah.
Yeah.
Is your turn your micro?
Pardon me. Oh, I don't have it.
It's right here on the table. So Daniel, Franklin here.
Hey, Franklin. How's it going?
Good. I was going to ask you about your Starship rodent coil combination. Are you still pursuing that route, or I know you showed it over there at the blessing ceremony. I was just wondering if you were going to keep working on that, or is that was kind of
Not really. Actually, what we found is that putting another an identical coil on the top and bottom,
Yep.
we're getting out pretty much maybe double or triple the amount of energy.
Yeah, yeah. I figured you would. Bucking, right? Bucking fields. Like the fields are bucking in the middle.
Yeah,
So what
exactly.
that says
Yeah,
is
yeah.
that we're approaching.
But what about?
One is wired opposite from the other.
Okay, okay. What about?
This little low load. So
And you're operating at a couple of hundred volts, right?
Sorry.
No. You're operating at a couple of hundred volts, right?
Yep. Right now we're looking at 332 volts out.
332?
Yes.
Forget that black meter over there, the little 300 volt meter. let's do an exchange here. I'm going to try and do something here. I'm going to match the output voltage, right, with U,
Okay.
so that we're operating at the same voltage, right? And find out what load at that voltage exists.
So that would be like a way of deducing kind of like the resistance in the LEDs. Is that how you say that, or is it impedance?
The impedance, yeah.
Yeah.
Yep. So that's the okay. We'll go up here, and then we'll go. Okay, now I'm going to go to. Okay, yeah.
Or it could be his bringing one.
Probably all of it together.
Yeah.
You think it would be better if I turn off my my oscillation here?
No, it's okay.
No, it's fine.
No, we've become accustomed to it now. It's almost like a friend. Oh,
It grows on
now
you
it
over
is.
time.
Now it is. Right, so now we're getting. Okay, this is 180 volts. We're not optimized here. Interesting. Your input current is measuring what?
Well, this way is measuring 0.89 milliamps, 0.089, excuse me.
input current. Right.
Input current is measuring
The AC,
657.
yeah, the AC input, so you're 52 volts and 187 milliamps?
50, let's just make sure. Yes, 52.9, and we're at 658 milliamps.
Okay. Now we're at 230 volts. Okay. Like watching 3 variables at once here.
Yeah. At school, like, you have so much equipment over there.
Mate, you haven't seen his garage.
Yeah, you haven't seen the bloody garage.
Mate,
Oh,
this is
my
a-
goodness.
1% of what he has.
Oh my goodness.
Yeah, this is... Well, it's tragic, it is.
It's like, Marty!
Warning! Out of control. Okay. So we're at 60 volts and 4. I'm trying to get this thing to resonate up at a fairly high value. Okay, there it is.
what was that signal you put into the neutron that starts big and gets smaller and smaller?
Oh, I pulsed it with the.
Oh yeah, we just ran it into a pulse generator.
Yeah.
That's not easy. Nothing complicated. Okay, it doesn't like to be open circuited.
Do you smell that ozone when you're driving it at this voltage?
The ozone, it gets canceled out when the capacitor's on there.
Oh, okay.
If you didn't have the cap there, it would start smelling though.
That's interesting.
Also, without the cap, the voltage kind of goes up a little. It's like you can measure spikes in like the 600 range without the cap. But the capacitor seems to make the load a lot more stable, and it makes the light a lot brighter.
Mm-hmm.
So I think the next step would be to get a real big, a heavy duty cap, maybe one of those $100 ones that they have on HV stuff.
What's that?
There's a website. It's highvoltagestuff.com. It's HV stuff.
Right.
So it's they've got these really big.
What kind of caps are you talking about?
I'm not too sure what it's a Tesla ham radio cap. Let me just pull it off.
You mean the mica caps?
I think so.
Because a lot of people refer to Tesla caps and they, they're smoking I don't know what. They're not, the types of things that work for what's called a disruptive discharge device is, alright, so we got 300 and 270, 80, 90, 307 volts. 307 volts into, it's into 8K ohms. Is that right? 8K ohms.
8K ohm.
300,000 8K. It's 11.25 watts, and I need a 50 at 50 at 6. So that's 38 and 11. So that's the wrong direction to do the impedance match. It doesn't want to go that high. So we want to go from, so that's 8K. I think we were getting close to what we wanted at about 1K.
So we still can't get unity.
Huh?
We still can't get unity.
Well, you can get unity, but then the coil is simply acting as a balun with a capacitor on the output.
A balun?
A balun.
What's balun?
A balun is essentially a balanced transmission line. So the only thing that would be different between what we're doing right now, where we have a resonant circuit bucking the voltage up at the end, and a straight balun into a low impedance load, is that we're now matching the impedance of the coil, and it becomes a series resistor to the supply. Right. So what goes in comes out, minus the losses in the series resistance of the coil. Right. And you don't really get much for that.
See, I've just changed the load here, and this is the same 192 LEDs.
Yep.
But the connection is a little different on this panel. This one has, let's just see, 2, 4, 6, 8, 10, 12.
Yeah.
So 40, so they're groups of 12, 24, 48, so they're groups of 48 and in parallel.
Okay.
So that's 1, 2, 3, so 3 groups of 48 in parallel. Actually, no, 4 groups of 48 in parallel.
And they're white.
Yeah, white. So it's telling me that we're pulsing it at 13 milliamps, and that really doesn't make much sense.
48. And we have 3.3.
Actually, 12 milliamps.
So you should be reading about 158 volts across that thing.
158.
What are you reading across the panel?
So let's check out.
6.8 for white.
3.3 to 3.5. You'll be somewhere between 150 to 170 volts. I'm guessing about 158.
You got 168. Or 168.
Okay. So the 3.4 volt LEDs.
Yes.
So, okay, that's good. That makes sense.
Excuse me, no, it's 143, so 143 volts. You said 158 at first, right? So it's a little under.
Yeah, I guessed around 158 for...
Okay, so it's a little under. It's 143.
Right, okay. And that's the AC voltage, right?
Yes.
Okay. Interesting.
So we're not, excuse my yawning, but I don't really sleep very much. But
You don't get to sleep. It's not a privilege allowed to.
It's good, but so unfortunately we're not seeing.
We're not seeing over Unity, no. Nope.
Okay.
Not on this setup. But I do want to do one thing that we haven't even thought about, or maybe haven't even wanted to think about. But I want to add a magnet to this thing.
Oh, Teddy boy. Johnny boy.
You've had a long night there, Charles?
Yes, sir. Yes, sir.
I'm gonna try and do something.
What's up?
We'll see. Yes. Nope. They ain't gonna help. This is a very strong.
Oh my god.
What?
Okay. Watch out for my laptop and camera.
Do you see this thing?
Oh wow.
This is neodymium boron.
That's huge.
It's huge.
What have we got here?
Huh?
Daniel, where do you see this?
So this near anything is
Very
very
dangerous.
very dangerous.
You can lose a finger.
You could lose a lot. You lose your mesh with this thing. Let's see. Do you see this thing? This is a neodymium iron boron magnet.
Wow.
It's about 3 inches diameter and about an inch thick.
Oh, jeez. That's a lot bigger than my biggest. We've got a 2-inch sphere over here.
Yeah, this is a honker.
That's, yeah. What is that, like 200 pounds of pull force?
No, I think it's actually more than that. The other one that I have on order is 6 inches. Whoa.
You got louder.
Hey, you did need a license for that, right?
You know, I think you should have a license for these things. Yeah, that's a hell of a magnet. Okay. Oh, that's interesting.
Not seen, man.
Now it's singing, baby. Now what do we got going on here? 60, 90, 120, 92, and we're at what? 1.9 kilohertz? And so we got 92 into a K ohm again, right? Mm-hmm. Except the current, what's the current? We're 52 volts in. Okay, 52 in. And 0.2. 10 watts in.
Mm-hmm.
And then we have 92 volts. Let me verify that. Distribution. Huh?
When you unplug it, when you change the noise.
Oh, I just shorted out the meter.
By mistake.
Yeah. Well, no. Just to get it to zero. It's a capacitor meter, right? So it can store charge. And it'll just sit there and give you a volt when there isn't one. Okay, so 92. 92. And then we have 1,000 ohms. 1,000 ohms. 846. And then Still not, it's not an over unit, do you think?
So the driving signal is a sinusoidal.
676 watts. And then we have 6. Yeah, it's what you see here.
Ah.
But you got your phone.
What? Oh, this is my calculator. Oh, well, that's the whirling dervish. That's the magical whirling dervish. That's him.
Okay.
He's doing his thing with the LED drive. We're doing it with a resistor, and we're having no converging match.
Do you think if we went and got some LED boards, we'd get any different response?
I'm not terribly confident of that. You have the 200 volt meter over there?
The one that.
Yep. Or is it here?
They're both over there.
There it is, yeah. I'm going to go back to the 200 volt so I can read this a little more accurately.
Sorry, things got fired in the process.
Huh?
So sorry when your things got fired in the process.
Oh, I am too. That was a very unusual meter. I wasn't paying attention. So that's.
Okay, so I've changed something up a little bit over here, and I think this may help you guys out on your end.
And what would that be?
I took out the capacitor altogether.
Yep.
And I'm running the same 52 volts on the input, now without the cap, directly into the lights, and I'm checking the amperage going into the LED panel.
Yep.
So amperage going into the panel, and you see it's not even very bright anymore.
Yeah.
So it's real dim.
Yeah.
But amperage going is 6 milliamps.
Yeah.
Into the panel, and there's 13 milliamps going into the coil.
Yeah.
Now the output voltage across this panel is 227, and the input is the same 52.
Right. Yeah, the reason that everything dimmed down is because you no longer have a resonance. So what you had before was a tuned transmission line.
Sure. So that's with the cap, and now just for the sake of numbers. So if we take that 228 that's going into this panel and multiply that by 6 milliamps, that gives us 1.3 watts. Right. So then we have the 52 volts on the input at 13 milliamps. And that gives us 676 milliwatts.
Right. And what was the other one?
Let me just 228 times 6 milliamps. 0.006, 1.3.
Right.
So that's without the capacitor at all.
Right. And that's a gain factor of 2. It's a gain factor of 2.
So should we take the capacitor out?
Maybe we should try not having the capacitor in line at all then. Because maybe if you drive this at a higher voltage, you'll see more resonance develop. and maintain the same factor. So maybe the capacitor is actually hindering the results.
Well, it usually does in a resonant system. Let me turn this off and we'll unsolder it. I'm going to turn that back on.
But exciting! It's not over yet.
It's not over yet.
No.
No, kids, it's not over yet.
Oh, this is far from over. This is the beginning.
Yeah, this is just the beginning.
Even if we find that it does work, we have to figure out how to scale it up into the kilowatt ring.
Well, sorry.
What was that coil that had the other coils wrapped around in the direction of where the plastics are?
The Starship coil?
Yeah, is that what that was?
Yeah.
What was that all about?
This Starship?
Yeah, is that whatever?
That to me, see. Nope. You have.
Let me see. Hold on. It's fuzzy, but no. Is that coils?
We had a rodent coil like
This one?
Let me see.
wrapped around. Yeah, that one.
What's that one?
The unification coil?
Yeah, what's that?
So this one has 2 layers of that ABBA design that you have there, and then another layer of the rodent coil overlay. And basically what we're finding with this one is it condenses the field to the center enough that you can sustain levitation on a magnet.
Yeah. Okay. Yeah.
So while spinning in rotation.
Right. But okay.
But that one basically it's I found that more wire it develops more resonance. So I'm not sure how you make sense of that.
You mean where does the frequency go?
Like more ohms. So if you wanted, I could swap it out with this one so that we can have
No, I was just saying what happens to the what happens
the frequency goes down.
Yeah,
so,
the frequency.
but it's also when I'm running the capacitor
Right, so the frequency should go down.
with more wire.
Yeah.
Okay.
Yeah. Definitely should go down. Okay, the capacitor is out of the circuit. Now it's out. So now we have a straight, non-resonant balun with a freaking magnet in the middle.
And I think the magnet in the middle will it'll change your resonant frequency too.
Yeah, probably. Yeah.
Let me just see if it takes away the. Yeah, it takes away the oscillation altogether.
Okay, now.
When I put the magnet in the middle, it removes all the resonance.
Then we take the magnet out of here, go back to 0. Put this somewhere.
You have to hold it up high.
Oh no, you gotta keep this thing away from bloody everything. This is very
I've got the big ones that slam together. The only way I could separate them was by wedging them in the door.
Yeah, when these things are in repulsion, they're totally uncontrollable when they in a repelling mode. You have no idea what's going to happen next. Okay, now we got 52 volts. No capacitor, so we'll go up to the next notch in frequency.
We're not getting anything out, bro.
What was that?
We're not getting anything out.
We're getting squat. out of this thing.
So you're passing the energy in opposite directions?
Yeah.
Okay, let me
Yeah,
give you
all I did is remove the capacitor.
Yeah.
Yeah.
So, let's see here.
What gave you the idea of using a capacitor in the first place?
Only because I found that when I put it on there, I was getting a lot more intensity out of the lights. But you know, right now I'm running it without the cap. So we're looking at. So I'm raising up this volume slowly because it's so we're getting more. It's getting more resonant now.
There we go.
So we're at 51 volts on the input, 52, and I'm getting a little battery failure. So 52. Yeah. Let's just get this tripod over here. This tripod will help me out.
Okay, with no capacitor, this is operating as a normal balun. I got 150 volts going in. And 250 cycles. You've got 100. What do I have going in? 150. And I have 142, 144 coming out. So that's into 1,000 ohms. 1.7. There we go. Another kind of low. And 0.14. 21 and 20.7. Yeah, so at 21 watts in, 20.7 watts out. So I've only got a like 300 milliwatt loss. But it's at 250 cycles, which means I'm sending it straight through a balun to whatever this load is out here, right?
So the frequency I'm operating over here
Yeah.
is 16.5 kilohertz now, and that's with it going direct
16.5.
16.5 kilohertz, and yeah, we have 10 milliamps going into this light at 250 volts.
Okay, what do you have as the primary voltage?
Primary voltage should be 52. Yeah, 51.4.
Who's this? Charles Fraser. Can't be you. Somebody's name, but I think Tyler 4 and 9.
That's a friend of mine.
Oh, okay.
But I don't know how he. He's one of the guys in charge. I'll send him the video.
Okay. He's in San Francisco.
No, he's in LA.
He's in LA?
Mhm.
Oh. Something said San Francisco on it.
Did it?
Yeah, so what I'm looking at is 2.3644 going in of watts and 2.5 watts coming out.
2.4 in, 2.5 out?
Yeah, 2.4 in, yeah.
Try swapping.
2.36. Yeah.
Try swapping your meters over.
Yeah.
You're not getting that.
No, using it as a balance, it's a balance. There's no gain in the balance. It's just a series lost in the balance.
Okay, so
we don't have an over-unit thing. Not that's of any measurable amount.
Daniel, are you getting this?
What was that?
So we're not in an over-unity thing here by any measurable amount. If we run it straight as a balun, it operates as a balun. It operates best at low frequencies. And there's probably, again, this is into a resistive load, and which would be the equivalent of light bulbs and phase-corrected computer loads. Anything that looks like a resistor.
So try, Daniel, try on your two meters, swapping them over maybe, and see if it's just like just take out where it goes into the meter, swap it over, see what the measurement is there. Then
Swap it over.
So pull out the where you actually plug in the positive and negative ends into the meter. Pull them out of the output one and put them in where the input ones are. So you don't have to move your meters, but just swap the probes around. Do you know what I mean?
Oh, okay, in for out.
Yeah.
Okay.
I think that there's probably an internal fuse on this one.
So you can fix it.
Yeah, maybe.
You would have thought.
You know. Sometimes you just need equipment. I've eaten equipment before. It's always distressing because you have to sit there and act like a jewel.
Yeah, same. We've got 52.
So Daniel has over-unity at his house.
400, and yeah, it's the same measurement. We've got some battery failure going on this meter, but it's reading the same exact thing as before.
Yeah. Oh, you put the cap back.
No.
What was that? No, the cap is still off.
Okay.
What I did was I just did what Charles said and just switched the probes over for this other meter, but it's measuring the same exact thing.
Right.
You're still at 16 kilohertz?
Yeah, in other words, the calibration on the meters is the same.
16.5, yes, the calibration on the meters is the same. So 16.5 kilohertz.
And
the 0.5 does make a difference.
The 0.5
If I go to 16 kilohertz, I lose resonance.
Yeah. And the
Just changing up.
Is there anything you think is accounting for this reading feature?
I'm trying to see what. Now the gain factor that you're getting is 2 to 1 or smaller than that?
It's smaller. It's so it's 2 point. I'm seeing 2.36 going in and 2.5 coming out.
Okay. So potentially you could have the way that the instrumentation is working on those meters. Do you know what the meters are rated for in frequency? Or
Yeah, these aren't TRMS meters.
yeah.
These are just the regular Radio Shack ones that I'm measuring with current with.
Yeah, and that's a possibility because that the way that those chips work and the way that they integrate voltages on the lower cost meters that aren't, things like Fluke 170, 182, Fluke 182, Fluke 77, the RMS meters that they have. Those are fairly responsive RMS meters that go out and go up beyond 20 Oh, see, that's one of the reasons why I use these. Is this is a true RMS measurement. It's an analog, and you can feed anything up to half of a megahertz in these things.
So this is okay. So I just changed out that meter that was giving us battery failure.
Yeah.
Let's see.
I like your setup. It's a good setup.
Thank you. So let's see. Can you guys see that? Is it in focus?
It says 2507.
25. Yes. So that's the voltage on the output. Let me just try to get this this camera on here a little better because it's giving me like a sideways pivot.
Yeah.
Okay.
529.
There we go. All right. Okay.
All right.
So we're at so it's 8 milliamps coming out at 250.7. So let me just do that again. 250.7 times 8 milliamps.
And when they bridge like that always?
We're at 2 now.
What's that?
This one was bridged across to this one.
Yeah, it was. And then, well, remember we went and disconnected the capacitor.
Okay.
Yeah, I just connected it.
Right now we're at 1.8 going in and 2 coming out.
1.8 going in.
Yes, 1.8 going in and 2 coming out watts.
Okay. So right there is 1.79 kilowatts.
Oh, I see.
I'm reading it on the meter over here. Right. And then, well, I can go up to 20 kilowatts.
Okay.
Yeah. So, it's got a built-in wing bridge oscillator. And then that bridge is across the back to the input of the power amp. And then the power amp is able to go up to 200 watts. It'll go from 20 hertz to 20 kilohertz at 200 watts. I have 4 of these things. These are like $2,500, $3,000 assemblies, and I use these for doing large 3-phase rotating fields around particle beam machines to see how susceptible they are to moving fields.
Hmm.
So I built these, 8-foot diameter Helmholtz coils,
Hmm.
and then put these things around the machine, and then linked a 3-phase oscillator into these things. And just spin a field around machines like this. And if there's any shielding problems around the electron beam, you'll see the electron beam do this.
Yeah, so now we're at 2.4 coming out, 1.6 going in. And the frequency is 16.25 kilohertz.
That's without the cap, right? Yeah.
Without the cap, yeah. Also, if you're not, I think maybe changing the polarities on the wires of the coil itself may change something for you.
Okay, we do that.
We'll bloody well do that.
Thank you.
Let's see. Bob?
Yeah, we have 10 milliamps coming out, 31 milliamps going in.
Is it one gun what?
Just remember George Harrison? Yeah. Happiness is a warm gun. Happiness is a warm gun. Happiness. It's not doing anything now. Why? You actually connected or not?
Oh, the capacitor.
Yeah, capacitors. Oh. No, that's right. Yeah, this is wires are touching. I don't want to touch my wires. Gotta keep them separated. No. Thermals. Okay. 60 and yeah, so I've got 11.4 in, 11.1 out. 60 volts in, almost 100 volts out. So,
We're not seeing over unity, Danny.
we're not over.
Yeah. Well, I'm getting at 245 volts. So do you think
245?
245 out? I got the meters on there pretty stable for you guys.
But look, the image is not sitting very flat. I mean, it's not in the screen. We can't see anything.
16 or
Which one?
You move the screen so that the meters are in the screen. We can't. They're cut in half, both of them.
Okay. Alright, so.
Yeah, no, there's no divisor on this one.
Okay.
Yeah,
Okay.
no.
1.6.
When you
Which
see that's
can't
color.
you see, Charles?
Neither of them. Both screens of the meters are cut in half. One on the top half of the screen, one on the bottom.
There you go.
There you go. There you go. Well done.
245. 52 and 245.
What's the voltage we're getting out? Like 100 volts.
Yeah, but we're not matched to what it is.
So it's 245 at 10 milliamps. 52.3 at 36 milliamps.
Okay, I'm gonna top this. Think.
Okay. So I see you're changing the load.
I'm changing the load. I'm upping the load.
That's something we've been seeing.
And now you guys should start smelling ozone. And if you're outside, you won't smell anything.
Yeah, probably not.
Yeah, I'm getting a little ozone.
Really? At that voltage?
Yes.
Mystery of all mysteries. 4K. 4K. Quarter at 52.
No gain.
I've got 13 and 6 out.
Okay, 13 in, 6 out. Danny boy.
Yeah, so I guess it has to do something with the LEDs. It's an interesting thing there.
Well, Kirkwood was giving an explanation to do with the meters that you're using. The chip there is sometimes like responds differently to voltage.
That's always a possibility. That the chip voltage, or the way that the meter registers an RMS value is not necessarily.
So then, what do you think is the issue with the ozone then?
I don't know about the ozone. That's a new one. See, air doesn't generate a corona until you're over 5,000 volts.
So then, okay, so then that means that. What about a magnetic field then? Could it just be the magnetic field that's
making ozone? No.
So what about light? So it's UV light does it? So what if the
ultraviolet light creates ozone? Yeah, absolutely. And if the LEDs that you're using are all white, then the reason that they're white is because the phosphor inside there is converting ultraviolet to white light.
But the ozone's coming from the center of the coil,
yes, and I'm smelling it right now, and we have these red LEDs on here.
I can smell it.
Yeah.
200.
I wouldn't know how to explain that. I can explain how the LED banks can in fact produce an ozone, but I can't explain how the coil could produce an ozone because the electric field around it is 20 times below the coronal threshold. So that's
some more testing.
Got me.
Oh my goodness. Yeah. So the plot thickens.
Huh?
So the plot thickens again.
Well, no, I'm going to do something. I'm going to take a electrostatic voltmeter, and I'm going to see if there's an electric field over this thing that we haven't noticed. Oops. Don't want to do that. All right, so I'm going to lift this and move that under so that it's
Not going to get. I see.
Am I doing it? Yeah, I did it. Okay. Good. Okay. Now, what we can do is put this above and below, the other. And we would need some.
Oh, well, that's a shame. We're not getting ridiculous amounts of overuse.
No.
sorry, the catch combination. Sorry.
No, I don't. No.
Terribly.
Yeah, have you, I've got his book with me.
Yeah.
Yeah.
The third one, that's the first.
Okay, how come we started with the third?
Because he goes right into it.
Does he?
He
Okay.
builds up to it. And he goes into it. My mother-in-law bought the book.
Really?
And then she told me about it. I'm like, okay.
Hey, brother Charles.
That's amazing.
We were going to share.
Hello?
Yeah, Charles, I've got to take a call right now.
Okay.
Can I jump back with you in a few?
Sure, bro, sure.
All right. Talk to you in a bit.
Okay, love, bro, love.
All right.
Hey, my bro!
Hey, guys.
Hey, how's it, brother Daniel?
Good. Sorry about that.
Don't worry, we are pulsing nanocarbon tubes.
Yeah.
Carbon nanotubes?
Yeah.
Oh, man. That's amazing. That's like the world's strongest material, no?
But, is it that?
We're just hearing a story about it. So what happened to
So anyway, when I was studying the nanotubes over at KLA, because I was building electron emitters out of them,
Wow.
I started looking at them and I saw the phenomenon.
Okay, you've seen it.
I saw it directly in a simulator, right? And I thought, holy shit, there it is again.
There it is.
There it is, except at this time it's not water. It's electron flow.
I got to see
He just found his book.
And so this is, I mean, it's in terahertz. This is a not only doing energy conversion, but possibly doing this thing we've been talking about, where influencing the surrounding area through pulse waves has potential merit.
What you got going on there, bro?
Work at night.
Well, I wanted to show Kirkwood something. He was right about the meters, and the meters were interacting with each other. I realized that when I separated them, the values changed on them. So I just wanted to go in and to tell him about what we're seeing, and then I also plugged in these analog meters that I found from when I had them before, and I never plugged them in. So I wanted to show him the input to the output.
Okay, could you give us just one sec?
Yeah, no problem.
That you could actually create extreme pulse functions, and all at room temperature.
Yeah. So taking a coil like that and making carbon nanotubes and spinning them
Because your body makes higher forms of carbon, I've been taught by like spiritual masters that I love. When you're in states of like higher states of consciousness, because they understand in the Buddhist and the ancient cosmologies that materiality is caused by mentality. So your desire to see manifests your eyes, your desire to hear manifests your ears. So actually the causal level is this like things like desire, aversion, and rather than those result in material. Certain type of energy flowing through you, your superconducting body, which is what it is, then you, the carbon that's in a very rarefied state, like carbon isotope 7 or something, and they say that like only isotope 12 is the basic structure or something like that.
Which
So,
it is.
yeah, well, they say that there's even like, so when you're in these refined forms of consciousness, your carbon takes on much more refined states, and that's the superconductor which your light body, which your energetic body is flowing through.
It's one of the ways that you have the ability to do constructive reconstruction when you're ill, or heal diseases when everything else has failed simply by sheer will. Your ability to visualize becomes manifest in purpose. Right?
Exactly.
You hear about this, you read about it, and then you see it. You see it happen. And it's you go, okay, well, I get it, I understand it. And it's so complex that the only thing that you can assign to it is the understanding that it's real. Not that you believe it, because beliefs all alter. Right? Is that you just look at it and say, okay, that's real, that's done. Yeah, good. If I have a need to utilize that, I know that I can. You know. So that's a cool thing.
That's very cool. And like to understand how nature uses these processes to create the vital force, like this vital force, and to make use of that to create energy that's harmonic and supports life. Is what Victor Schauberger was doing.
Okay, that's sharp.
Yeah, so he understood water, and water is using the sacred geometry. It creates this implosive field.
Well, you've seen what happens to waters of Japanese.
Masahiro, I looked after him when he came to South Africa.
And you see the
He's gone.
did he go inside?
Yeah, unfortunately.
Bastard. When you see this Japanese guy who shows the form of water crystals.
Yeah, dark ray microscope.
Yeah.
Masahiro Moto. I looked after him when he came to South Africa.
Really?
Yeah.
Oh.
Schauberger is just like light years ahead of this guy, and he lived a long time before.
I know. I was just fascinated with the fact that he had found the relation between water and living emotions.
Yeah, the vibration
Right.
of a thought.
Yeah.
Daniel wanted to show you something. Have we still got some
Yeah,
time? Hey, Danny.
Hey guys, sorry about that. Before that, I had to drop off.
No worries. How's it going?
It's going really well. I just plugged in some analog meters onto this onto the system, and I plugged everything in to the best of my ability. And I also discovered that Kirkwood was right about the meters, and they do interact with each other. So moving them away generated a more steady meter reading over here. So I just wanted to
use analog ones, right?
What was that?
You're using analog ones, right?
Yeah, so we have, this is the output, and this is going to be the input.
Okay.
And this is the input amperage, and this is the output amperage. Along with the digital voltage reading with the TRMS meters on the top.
Okay.
And then I also have the lights plugged in, so I'm measuring the output energy into the lights.
Okay, so how does it go? What do you see?
Well, basically what I wanted to show you right now, they're the same. So as I tune it, I'm getting into back into resonance, and you're going to see that analog meter going up.
Probably more out here than we didn't have to search much for much.
Okay, yeah.
Okay, so now we have lights on.
This is good.
This is alternating current. Alternating current going through both of these meters. The currents are the same. You see that?
Okay.
The current is the same.
Yep.
The voltage is stepped up. And also the analog meter showing us that there's more power there. So that's the input. This is the output.
What is that volts?
So we're measuring 1,000. So we're measuring 1,000 across the analog meter. And you see that we tune it. And it goes up and it goes down. So we're actually measuring the power there. Input, output.
So why is this happening with your coil, but we can't replicate it here?
Same current.
Yeah, it's magic.
That's very curious. That's very curious.
What frequency are you using now?
Right now we're using 16.3. You know, maybe I just have to make you guys a circuit. I'm thinking that, you know, to eliminate all the complexity, just make you a circuit that works. And also, possibly, you guys really need to oscillate the same panel.
But he's getting clearly, he's showing on his things, like his output is way higher than his input.
That's the input power. That's on the analog meter. Same current. And it's steady. That's the output right there. Greater than the input.
That's what, the voltage?
It's the same amperage. And the voltage is 257 on the output and 48 on the input.
Right.
And it's not induction either. Its energy is going in opposite directions.
The AC meters.
We're using 16.3 kilohertz there.
Right.
And I also have the measurement on the scope. So input is blue. Input is blue. Output is yellow.
Right.
I'm not sure if it's...
Yeah, I see it. I see the band in the middle, yeah.
Yeah, so that's both the 10 volt scale there. This gives a pretty cool little tool that allows us to measure. So we can go in and set the measurement on there to read the voltage.
What was it you wanted to say, Coco?
So I'm going to put peak to peak.
I was going to say the voltage reading on the meters, both the current and the voltage reading on the meters. Is this AC, strictly AC drive?
This is AC.
And do you have a constant amplitude signal generator?
So this is the signal generator. We're using the Rigol. It's a DG1022.
Yeah.
Rigol DG1022.
And it's a leveled output, right?
It says 5 volt peak to peak input.
Right.
Phasing is relative, right? So
Right.
16.3.
But you can sweep from what frequency to what frequency?
Oh, it goes up to 20 megahertz.
Okay, perfect. So, and it'll establish a constant amplitude, right?
Constant
constant amplitude at any frequency, right?
Yeah, so it's a set output.
Right. So one of the things you want to test is the meters that you're using. Is hook the meter just directly to the output of the generator, and sweep the frequency from like 100 hertz to 5-10 kilohertz, right?
Okay.
And see if the meter reading for voltage is the same for all the frequencies. If the
okay, I see what you're saying.
Right.
I see what you're saying.
So, we're assuming that the output voltage on the generator is a constant amplitude. So
I see what you
to
mean.
check the calibration on the meters to see if their resolve is the same, is just see if they read the same voltage at all the different frequencies.
Sure. So
There's a point where it'll roll. There's a point in the meters where they'll roll off, and it'll read less voltage than what's there, or more voltage than what's there, depending on how the circuitry behaves to frequency.
Okay, so
Right.
basically I've just got to get a different probe that doesn't...
Right.
My other
But the
probe is...
meter has to go direct to the output of the generator.
Okay.
Like a BNC to a couple of bananas.
Yes.
Right.
I think I actually have a BNC over here.
Yeah.
I'm just trying to... I have
A BNC to a 3/4 space banana jack plug.
Okay.
Because
So I've got...
the 3/4 space plug will plug right into the meter.
Okay, so I've got the... that's the input back there. And that's coming directly off of the signal generator, right? So you mean just to measure this meter, this output?
I think that's what he means, directly from the thing.
Okay.
I don't quite understand why.
So I'm gonna do that though. Okay. So we just want to make sure this is the set 5 volts, correct?
What's that?
we just want to make sure this is the set 5 volts that it's saying that it's output.
Yeah, because you know there's a lot of those meters. I mean, I use them a lot at the lab, but I only trust them if I test them.
Okay.
I don't believe anything.
Yeah.
You know, it always comes back to bite me if I do.
You gotta be sure.
Doing good. Doing good, lad.
What you do is giant sheets of copper.
We'll take them into the shop.
Work out.
Huh?
I think maybe I should just cut it. Yeah. That should work. Sorry about that. I've got this little complication going on here with my signal generator being in the most awkward position ever. Okay. So this is the voltage on the input from the signal generator. So let me just get that into here. Okay, so that's 671. So it's a constant 671. You guys there?
To see how high a frequency. No, those are going to stay in the house.
Danny, how you doing?
I'm doing perfect. Yeah, I got the answer to that question. It's a solid solid 675 millivolts going into the amplifier.
Yeah.
And everything is looking perfectly stable.
Okay.
So the electrostatics all go in because.
Well, Danny boy,
It's good the way it is.
Oh, okay. Yeah, I thought
you are the magic one.
Huh?
Danny's the magic one. All right. Well, look.
He's got the magic. He's got the magic.
Maybe we're going to have
that
to
might be
fly
okay.
you over. My mum says
Yes.
we have to fly you over to come with your stuff and work it out.
All right. Yeah, that sounds great. Maybe that's just a better idea because I mean, I don't know. It looks pretty simple to me. I don't know.
Over Unity looks simple to me. Yeah, lucky you, man. We just spent ages trying to get it working.
Well, I could switch out this coil. You want me to try? I have another identical coil to this one. I can try switching it out and showing the same thing with a different coil.
Okay, okay.
Would you like that?
Well,
Is this going out back?
I don't know.
Yeah.
I think we're doing okay, but I mean, if it's exactly the same thing, well, go on, do it for fun.
Well, it's the same thing. I already did it plenty of times. I don't really need to do it for fun, but... You know, unless you guys wanted to see it. That's the only reason why I would do it.
We're trying to tidy everything up. He brought out so much equipment, did Kirkwood. But look, I don't understand how come you were able to recreate over Unity and we can't.
Well, I guess we would have to have the same exact test equipment, and if we're testing with a load of 192 LEDs, I'm pretty certain we have to use that same load to recreate the same effect. We can't use a variable resistor. So we're dumping energy into a resistor expecting the same effect as we're getting from light-emitting diodes, and that really doesn't make very much sense if we're trying to replicate the same thing.
But it's a load, isn't it? Can't you get that effect?
Not with a motor. So if I plug in a motor, I won't get the same kind of resonances.
So Daniel's suggesting that maybe because we're using a variable resistor, it will change the kinds of resistances that we're experiencing.
Of course. Yeah.
Compared to having LEDs and the resonances.
Right. Right.
So do you think that could have an effect? Danny,
Well,
how about Marco?
Plugging in a motor, and I can show you guys if I plug in a motor, I lose the power altogether.
Okay, he says if he plugs it into something else, he also loses all that power.
But you know, in an LED, there's not a linear load.
An LED is non-linear load.
And maybe that's why it's working.
Yeah, and that may be the case.
So as long as, to me, I just feel like as long as it's a working system, then we have to recreate what works.
Right. Yeah. But then all of the energy gain, let's assume that there's an energy gain there. It can only be applied to a nonlinear system.
Yeah. So that means only LED lights, and if that means that we could...
well, LED lights are something equivalent to that, yeah.
What else is a non-linear system?
Plasmas are nonlinear, very nonlinear.
I love plasmas. I would love to do. I always wanted to do more with plasma. Well, everyone's thinking, where's my plasma?
Do more with electric arcing at low voltage, exactly, to excite plasma.
It's innumerable.
Really, you can propel things, can you?
Oh yeah, you can propel things. In fact, I'm mentoring a graduate student over here at San Jose State. And his project is a levitator, high voltage levitator.
Well,
you know, like the Nodden type stuff.
So it's tinfoil things.
No, he's going further.
Really? Oh wow. Plasma?
Yeah. No, it's not a plasma levitator. Okay. It's an electrostatic. It's more of the T.T. Brown type.
Right. Using
Thomas T. Brown.
If we can fly Daniel over to set it up, would you have a look at it?
Oh,
yeah. Come for lunch.
Where's Daniel?
Lunch is on us. Daniel's in New York. Daniel, we found.
He's in New York. Okay. Yeah.
Daniel, you can fly out here for like $100. Marco Rodin was showing me. Marco Rodin finds the cheapest flights in the world.
No kidding.
Check out
it. That's great.
Check out.
Because this really matters, though, is to have like a complete expert particle beam physicist to be able to say like yes or no. So. If you reckon you still got it, Daniel, then I reckon let's put on a lunch for.
Well, it would be a good idea if well, he's made an art of building these coils.
Yeah.
So.
Nobody makes them.
Mm-hmm.
Was this coil
made by
built
him?
there?
Yeah.
Okay.
That's right.
Okay,
Everything that was built on site over here. The only thing that we didn't have built here was the black frame for this particular unit. We've made frames from scratch as well, though.
Yeah. No, I love your frames.
Thank you very much. I appreciate that.
The only thing I can think of is to drive it non-linearly and introduce nonlinear into it and see what the nonlinear response.
Yeah. Have you got something at your house that we can play with?
I got a outer ignition coil. Pulse with high voltages and.
What we got to work was a. Let me see if I can just show you. This was working. This little unit here was doing a good job at driving it.
It's a neon transformer.
Yeah,
Or
neon
ballast.
transformer. the only thing that we found was that
Sorry.
it was creating a lot of radio waves, and right now this setup doesn't create any radio waves.
Yeah, it's a magnetic.
Right. You mean the sine wave drive?
Yeah.
Yeah, so we have this this meter.
That's why the one I'm playing with, I have a little cone inside
Uh-huh.
a big cone.
So we
So
could
the
set this to radio
the big
wave,
cone catches it.
and we're not getting any cancer
cool.
emission there.
No, you wouldn't. Not the way you're driving it now.
Yeah. So then the other one, it was producing a lot of that, and
Yeah, it's a switching power supply. They have quite a high emission.
So Daniel, are you saying that if we use a linear load, you don't get over unity, but if you use a non-linear load, then you do get over unity?
we get the over unity with
That's what it's saying.
this amplifier here.
Okay. So do you gentlemen feel that?
Well, no, that's. Oh yeah, but the load is LEDs.
Yeah. The non-linear load.
Nonlinear.
Do you feel that it's worth pursuing this to look into trying it with a non-linear load?
I could try switching this to a fluorescent tube if you'd like, and you could see what the measurement is there.
Yeah, I got one.
Yes, I do.
You're the man.
Thank you. So are you guys?
So what size tube is it? T4 or T8?
What was that?
Is it T4 or T8 tube? Which size fluorescent?
Let's see. Is this 15 watt? Does it say it on there? It's T8. Yes.
T8?
Mhm.
Yeah. Is it 15-inch T8?
Would you like one a little bit bigger? Well, I have a 40 watt on hand also.
Yeah, use the 40 watt. Yeah.
Okay.
Yeah.
So let me just go and grab that back
Try to set
there.
it
Try not to
So cool, isn't it?
It is.
try not to break it.
I like their.
It's some business shit.
They had an open
Yeah,
competition
there you
with the
Okay.
U.S. government on an antenna, and they won.
Huh?
That coil they had. They won a competition for sensitive antenna.
For what?
For government project.
For what? For use.
I don't know. Whatever they took it for, but at least pretty sensitive. I don't know. Daniel, you would know more about that.
The one that I was using for field searches that I came up with was a spherical coil.
Oh.
And yeah, it works. It's perfect dipole. That's a perfect dipole.
It's like
It's a bitch to wind spherical coil.
how big was it?
It's 4 inches diameter.
Oh,
What's going on, Danny boy?
He's gonna light up.
Just
his
trying to
fluorescent
get
tube.
these wires on there without messing things up and making it look too messy.
What's that coil in the middle?
It's a dual.
Oh, this is a little pickup coil.
Oh, okay.
Okay, now let's see when this tube turns on.
It should turn on at 277 volts.
There we go. Okay, so maybe I just have to kind of help it out.
Yeah, it needs a capacitance underneath it.
Okay.
There.
A capacitance underneath it, could that be like a material? Of
Yeah, like a piece of aluminum foil or something like that. It helps stabilize the plasma until the walls are warm.
Okay. So yeah, this is what we're seeing now. Then this is the meters the same. So we only have 4 milliamps going through,
transformer.
but there's still more power on the output than the input.
What is the
14 milliamps.
0.9. No, it was
what's that?
0.014.
That's 50 volts and what?
So it's 50 volts, 14 milliamps, and against 218 or 219 and 4 milliamps. And that's lighting that fluorescent tube.
And the waveform is sine wave?
Yes, still sine.
Still sine.
19 and 0.4.
So I'm just going to try to change the voltage on this.
19 to
Or there we go.
Okay. And then, what's the square wave?
That's the input.
To what?
To the coil.
That's driving.
That's coming up. Yeah, that's driving the coil.
Oh, I thought you were driving the coil with a sine wave.
It is a sine wave, but it becomes kind of squared out as I increase the volume. So as you can see it just squares out past a given point.
No, you're hitting the limits of the amplifier.
Yes.
You're hitting the rail limits on the amp.
So he's going from linear to nonlinear.
Okay,
As he's
so the
driving.
whole RMS equation for the meters is different for those two waveforms.
Yeah.
Yeah. So I'm not convinced yet, because the measurement quantities by the meters are going to be different for those two different waveforms.
I think we actually have to make a whole new line of meters.
Well, it needs to be a true RMS meter, where what you've done is you take the square root of the square of the voltage, the integral of the square of the voltage, and that generates a true RMS value. The other way is to
So
do
what
it.
about the analog meter on the input? Does that not
No.
satisfy anything?
No, because the analog meter or the digital meter, either one, they respond differently to a square wave than they do to a sine wave, than they do to a pulse, than noise or anything else. So all of the values are, you see what happens when you run the capacitance by it?
Yeah. So what about if I input a square wave instead of a sine? Because I could do it pretty much with anything: square, sine, ramp.
Yeah, and then you take the square wave and take 1/2. Let's see, you have to take 1/2 the value peak to peak, and then take the rise time that you see on it, and whatever that duty cycle is to the DC value of the 1/2 peak to peak. You have to take that portion of the duty cycle and take half that voltage, and then sum that with the other. Integrate that with the other. That bulb is just barely on.
Yeah. I mean, the power is there though. It's
Oh
a
no, I
negligible
understand
amount.
that. Yeah, the power's there, but it's. I can see the capacitive effect of your hand.
Yeah, it's not really doing.
Every time when you do that, you draw the plasma toward the to conduct from both ends.
Let's see if I change this to square. Now it's on square.
Yeah.
It's pretty much generating the same exact wave pattern.
Yeah, but the way it gets measured is different. You can see the capacitance effect of the draw.
It's like having a lightsaber.
Well, in my garage, I mounted up these fluorescent lights that have no ground. So what I do is I tape a piece of copper strip on the back of that fluorescent bulb, and it goes in and just lights up.
Yeah.
You know what I do like also is
It
that
has to have that couple
Okay. To make it fast light.
to actually make it strike.
Okay.
Yeah.
Okay.
so this is the power
need a
coming from the amp.
So
So we're running 24 watts right now coming from the amp. 24, 23.
What's the
That's
frequency,
discern,
Kenneth?
and I'm going to stop the amplifier from running. I'm
What's
just
the
turning
frequency?
the sound frequency.
Oh,
So that lights up and creates that power with 2 watts.
I have kilowatts. That's actually a pretty good meter for kilowatt. Per centimeters.
So, what do you think's going on?
It's instrumentation.
Yeah.
That's what
It's what?
I think it's instrumentation differences. What's called instrumentation?
Oh, okay. Why you guys can't get the same exact thing on your end?
No, he's saying he thinks you've got instrumentation error.
The kilowatt meter from the wall?
Yeah.
He thinks that the kilowatt meter on the wall is wrong. That's interesting. I can plug in a soldering iron to try it out.
No,
Right into the outlet.
no, I don't know. How about this non-linear load business?
What's that?
How about this linear or non-linear load business?
I have to think about that.
Well, gentlemen, I kind of would like to think that we're looking at slightly new physics and things that have to be readdressed in a different way. And also, we might have to open up a whole new line of meters because this is not the first time that we encounter these occurrences. So, yeah, it's something that we have to tackle from a whole different way of thinking.
Okay. All right, you're inside now. It's warm inside. So Danny,
Of course, then Edinburgh is even worse.
Kirkwood's got to think about stuff.
It's a lot to make a decision if there was to be made.
I could run all the equipment outside on an extension cord and do it from the backyard.
No, don't worry. Look, I think Kirkwood's going to think about it all and see just.
I
Sounds
think the
wonderful,
majority
guys.
of the difference is the instrumentation.
So what exactly do you mean by instrumentation differences on my end? In terms of amp log and the meters, what meters would you like for us to purchase in order to satisfy your...
Well, it doesn't matter to me. It's just that you need to have a true RMS meter.
We have 2 here.
Which ones?
These orange ones are TRMS meters, and they're measured for a... Let me just get the specs on this. These are the Klein tools, MM2000, and if I flip it to the back here, it's measured up until 1,000 volts.
No, that's not the part that I'm wondering is what the conversion algorithm is for that meter. Is it
Yeah, I'm not sure about the technical specs. All I know is that I had someone suggest that I buy a TRMS meter before.
Yeah.
And I went ahead and did, and it didn't really show me anything different than my Radio Shack meters did.
Yeah.
We're seeing the waveform on the scope. We're seeing the power output. We're also seeing it on a kilowatt meter that's plugged right into the wall. So as far as I'm concerned, that works. So, you know, it looks like a new science that has to be revisited with a different perspective. And that's the way we're going to understand it.
There's something that is anomalous between, you know, to actually do the measurement is a lot. If the differences are small, then the measurement techniques need to be highly refined. If the differences are enormous,
amplifier.
huh?
There's a clear indicator of 2 watts being drawn from the wall. There's 2 watts being drawn from the wall. As soon as I turn this frequency off, it drops down 2 watts.
Yeah.
Turn it back on, and there's 2 watts of power. On the output end, we're lighting this 40-watt fluorescent tube. And we're doing this all in a 1-to-1 ratio, and that doesn't even exist on the planet. you shouldn't have a 1-to-1 ratio stepping up, whether it's a resonant circuit or not. 1-to-1 ratios do not act as step-up transformers. So either way, we're looking at something new. Aside from that, we have an ozone phenomenon that we can't explain either.
Yeah,
So,
that one. Well, that one's. It's possible from. Franklin and I were talking about that with the center of your coil. If there's an intense magnetic field there, which there probably is, oxygen is paramagnetic and will pair up into ozone O3 under a high magnetic field.
You know, and that's what these coils are designed to do. They're designed to have intense magnetic fields, and we can levitate magnets in the middle. So
the other place that the ozone can come from is that when you pulse LEDs at much higher currents than are normal for the routine current to run it, like 30, 40 milliamps. When the peak currents are more than 2 times the rated current of the LED, the phosphors go into saturation and excess UV comes off of the LED. When that happens, it creates ozone.
And you said that that's with the white, correct?
That's with the white LEDs because the wavelength of the light is below 409 nanometers.
But I could tell you for certain that I've achieved that with not only white, but also red and orange and blue and green.
Right. So if the ozone is still produced, if the ozone is still produced, then it has to be produced from the high magnetic field because there's no coronal potential voltages anywhere near your stuff. The only thing that can affect the oxygen is a high magnetic field.
Okay.
So
if we look a bit more into this linear load, non-linear load kind of business, he says that if he puts a linear load on, he doesn't get much.
He doesn't get over units. That's right.
If he does, then he doesn't. If he does put a non-linear load on, then he does get over unity, and if he doesn't, he doesn't.
Right.
So I don't know. Why don't we just get some sleep and take some time to think about if we could maybe present to Kirkwood. And
these are the ones he's using.
Yeah.
Kilowatts.
Yeah. Okay.
These are not RMS devices.
Okay. Okay. But it.
But they work pretty well.
Okay.
For everything else.
Okay. So, but look, man, you got to decide if you want to. Kirkwood, would you be open if we got you the nicest supper one night?
What's that?
In like a week, give you a week respite, and then we can get Daniel with one of his coils and can come out here and have to give his best go because
It's a possibility, but I have to check the schedule.
Okay, of course. Otherwise,
I might not be here.
Okay. So until we got until the 6th of November is when I'm going to head home.
Whoa. So what?
Of November.
6th of November.
So it's like the 20-something now.
Election day.
Is it? Okay.
Yeah.
Good to
Isn't that right?
Yeah.
Election day.
All right, Danny. I mean, it would be Daniel. It'd be really good if we could get
put my brother back in office.
Kirkwood's measurements to verify this because he's got the best equipment here.
Is it the best? I mean, it's not measuring the same thing that these simple meters are.
No,
they're not reproducing the same effects. So I think that we have to maybe plug in things the way that I have it plugged in here, and maybe you guys, it would be a little bit more cost effective as well, just to go and grab the same meters and see what's really going on.
Oh yeah.
Okay,
that may actually save a lot of time and travel.
The meters.
You're absolutely right.
The meters that Kirkwood has are like,
they're just RMS deals.
They're RMS and very they're analog, so it gets rid of a lot of anomalous kind of.
I've got 2 analog meters here, Charles. So I can just show you that again, and we're still reading the same kind of over unity with the fluorescent tube over the LED panel, and we're only pulling 2 watts of power. So you know, as far as I'm concerned, it's a working unit that puts out more power than what goes into it anyhow. Because as Kirkwood stated, it needs a certain voltage to even ignite this tube. So you know, for me, it's like I'm seeing the light right now.
Yeah, usually the starting voltage is that a 4-foot tube?
This is looks like a 3-footer.
Okay. The 4-foots usually start around 277 volts.
Sure. So, you know, would you agree that it wouldn't turn on with 53?
No, never.
Okay, so that's pretty much my
you've
point.
got
And I'm
voltage.
looking at a steady current reading on the input.
Right.
That's showing me that my power on my input on the analog meter is less than my power on my output on an analog meter. And I'm also looking at these TRMS meters, and they're telling me exactly that what Kirkwood is saying is true. At 200 volts plus, we have light. So this is what we're looking at, and we're only pulling 2 watts of power in the process. We can turn it on and off, and we can pretty much do the same thing. This is
Okay, the thing is like it's not an RMS meter on the wall. So what we're trying to do is just really have a look at this with the best possible equipment. That any criticism of this can be dealt with and explained. Like, no, we've used the correct instrumentation for measuring it.
I see what you mean. Okay.
So
Well, yeah, that makes perfect sense. So maybe it would just be better that I just go out and get the meter and plug it in on my end, and demonstrate that our unit is working because we have the correct setup and that one that's ready to replicate it over and over again.
It's the one thing that's going to prevent a lot of discussion.
Yeah.
Because there's always going to be the physical proof that needs to be done with something's more than,
So I can
more than
prepare
that
it as a setup, and you know, I can instruct people through this. There are replications in Russia, Portugal. There's one in Kansas. People are showing that these coils work all across the globe.
Okay, but do you get the principle that if
I understand the principle of the watt meter needing to be a TRMS value, and I also can predict that in the future, once we do get this watt meter that's TRMS, it will say the same thing that this watt meter is telling us right now, that we're only using 2 watts of power to light this 40-watt fluorescent tube. And I've done this with batteries, I've done this with all different types of amplifiers. This is not my first roadshow. I've also talked to a number of electricians before, and we've seen the same thing on a number of different oscilloscopes across the globe. So, you know, for me, this is just something that I'm trying to help you guys understand, and it's all new technology that has to be viewed with a different perspective because it's not standard.
Dude, thank you so much, and we appreciate it. Don't worry though, like, this is just part of the process, man.
Sure, I've been here before, Charles. So yeah, if there's a watt meter that Kirkwood would suggest that we go out and buy, that plugs into the wall of a TRMS value that would satisfy his viewing pleasures at least, then we can go ahead and do that, and then I can have a watt meter that I can suggest to you that you can replicate on your end.
Okay, thanks very much, Daniel.
Wonderful, guys.
Okay,
Thanks for
cool.
taking the time.
Thank you very much, bro. We'll speak to you later.
Take care.
Okay,
Bye-bye.
thanks a lot, bye. Hey, bro. How's it going? Hey,
I just want to, I drew up a slightly different diagram to show Kirkwood.
Okay.
This is the over unity measurement, so I just wanted him to see it in operation.
Okay. Can I show you? Daniel was just saying he's drawn up the diagram for over unity again, and he wanted to show you the thing for here. I'll put it here. He wanted to show you the experiment they did for over unity.
Hey, Kirkwood.
Hey, how you doing?
Good, good. So, yeah, just let's see if I change this lighting.
Well,
So, let me just go over what it is that we have here. So we have 56 watts coming from the wall.
good deal.
So 56 watts coming from the wall, and we're operating 2.1 kilohertz.
Hold on. He's
I'm gonna get my camera.
just going to get his camera.
Okay.
We're gonna duplicate everything you've got here.
All right, sounds good. Yeah, I was hoping that this would help you guys out in doing that.
Yeah, why not? Life is good when it gets clear.
Hold on. It's come out. Yeah.
Come on
There-
out.
Come
there
on
you go.
out.
There you go.
Just, that's it.
And
That's
there,
it.
got it.
Hold on.
We're good.
Okay.
Yeah.
All right, so we're operating 2.1 kilohertz, and I'm checking the voltage on the input there,
Yeah.
and that's 53 volts.
Yep.
And I'm checking the amperage going into the
676.
coil on channel 1.
Yep.
So that's 676 amps. Well, it fluctuates, but
Yep.
that's roughly what we're looking at here.
Yep.
So
Nice.
there is an amp drop on the output. It goes down to 654. So you see, it's generally 20 milliamps less on the output.
Mm-hmm.
But the voltage is it's going up from 52.5 to 335.
Right.
And that's only because we're oscillating this panel.
Yeah.
So it's 192 LEDs in series.
Right.
So that's what creates a big field on this.
Where's
And,
your-
let
where's
me
your-
just show you the
I didn't
field.
see the capacitor in your drawing.
Ah, you called me out. That's it. Yeah, it's right here.
All right.
He redrew it.
Thank you.
Sorry about that.
And 0.15, right? All right.
Yeah.
So we've got 0.15 2 kV film cap.
Oh, excuse me. Hold on. So I'm measuring the, that's not where I'm measuring the amperage. I'm measuring the amperage from here, going into the cap. So directly from the output of the coil to see if there's any loss in amperage on the output of the coil side.
Right, but the phase angle is going to be different now. So you need to move the meter over to the load side.
The amperage?
Mm-hmm. Actually, to move it to the way your drawing actually shows it.
This way right here?
Yeah, well, right now your drawing shows the amp meter to the right in series with the load.
Okay, yeah, no, the amp meter is not in series with the load.
Right.
It's first going, let's see. It's first going through the cap, yeah.
Right, so you got to run over the load, and the reason is you're going to have a different current on both of them. The reason you're going to have a different current is because you've got a different phase angle running directly into the cap than you do with the load.
Okay. I see what you're saying. So effectively, we just have to switch this around, right?
Yeah, just put the ammeter in series with the load. The voltmeter should also be directly across the load after the amp meter.
Okay, so not on the coil output.
Yeah, not on the capacitor, but on the load itself.
Okay.
That way, you have a full instrumentation to the load, right?
So we're not checking the coil properties now, though, right? So
No, we're looking at the properties of a black box. What goes into the black box, and what the load sees out of the black box. Right?
Okay.
Because the thing that you're doing is you're measuring the RMS values, but there's no phase angle. And the phase angle changes the relative power measurement If the phase angle was 0, no problem. But the phase angle before that cap is not 0. In fact, it's probably more like around 45 degrees to 60 degrees, right?
Before the cap?
Yeah. So, and you know, we have a phase angle meter upstairs. We could actually look at it in both directions. Yeah. Okay.
So I've just got to change around this cap then.
Very exciting. Very exciting. You don't eat your skins?
I sometimes do.
Okay.
I was just.
If you're not going to eat it,
Your mama's gonna get if you don't eat your skins, you know.
I will eat your skins.
What are you guys eating over there?
We're eating salad and taters.
Nice. That vegan.
Sweet
Yeah.
potatoes.
Yeah.
Kirkwood called and asked beforehand, so I was like, yeah, man, just the ones that are designed to be eaten. He's come out with the goods, man.
Do vegans eat?
I don't know what that means, designed to be eaten.
Anybody want the bread and stuff?
No, you have it, you have it.
I'm good.
Bread
Thank you.
Yeah, we vegans eat a lot.
Yeah, we do.
We have to, right?
Yeah. I love eating a lot of fruit, man. Like eating 5, 6, 7, 8, 9, 10 bananas.
Really?
Alright,
All at
that's-
once?
You drink
Oh.
almond milk?
Yeah, I love the almond milk. Hooray! Oh, we're getting so close, Daniel.
That's right. That's
my
right.
little heart is just like.
It is happening.
It's a lot of work you've done so far.
Yeah.
It's very good.
Not easy getting.
This is just no vanilla or anything. It's straight.
All right. Thank you, sir. Delicious. And the Beatles. I was listening to the Beatles all morning. Oh my god.
Funny.
The Beatles.
Wow,
Peaceful
You
people.
want to try some?
No, I'm good. I'm
Is
good.
that right?
It's perfect. Thank you.
That's the closest one that I found for the one that they sell at the farmer's market.
Have you tried almond and coconut milk?
Yeah. Yeah.
Together?
Ah, that's wow.
My wife doesn't want to eat coconut.
Why not?
Huh?
Why not?
Because of the saturated fats in it.
Really?
Yeah.
I had that very, very good for you, those fats.
Well, the cord is still out of that one.
Okay.
So on the side of keeping peace, I avoid the coconut.
What's that noise, bro? Is that the...
That's the coil.
Yeah.
2.1 kilohertz.
You can
This
tell.
guy's got perfect pitch with frequencies, bro, not just with notes.
Wow.
Yeah, we're using nothing but harmonics of 3, 6, and 9 over here.
3, 6, and 9 what?
From the fundamental?
From the fundamental.
From
How do
From
you
the-
use them?
3, 6, and 9. From so we're running 2.1 kilohertz. See, so this is all right. So now it's saying we've got 0.88 milliamps going into this load, but that doesn't make sense now because we have a tremendously bright load.
Well, he was explaining that earlier.
What's that?
When you...
The brightness of the LED.
Yeah, when they get much brighter when they're oscillated or something.
Yeah. Well, when
So-
they pulse.
When they're pulsed.
I see.
Oh no.
What?
0.88.
So it's gone right...
Look at 0.88.
So what was it before?
Well, it was at 640 before.
Yeah.
640 milliamps.
And now it's at 0.88.
That's 800.
Now it's at 0.88.
880 milliamps?
0.088. Excuse me.
Oh.
0.088. So 88 milliamps versus 667 milliamps. So that's what's coming out of the capacitor going into the lights.
So if you times your volts by your amps, what do we get?
So let me see here. So we're at 336 times 0.088. That leaves us with 29.5. 29.5.
And what was going in?
So the total wattage going in, so we're looking at 29.5 versus 52 times 0.667. So we're looking at 34. So it's saying that there's 34 going in and 29 coming out.
Oh.
But that really doesn't really make much sense. I mean, considering
what?
The brightness.
The brightness. Kirkwood's explaining that when they're pulsed, the LEDs get much brighter.
Yeah, I mean, I can understand a little bit brighter, but we're also getting like a lot of heat coming out of these bulbs because we're pretty much pushing them to the max. So, I mean, each one of these LEDs is 25 milliamps a piece.
Right.
So if we're only running 80 some odd milliamps to drive the whole entire panel of 192 bulbs, I don't think that makes too much sense now.
How many rows do you have in parallel?
How many rows do you have in
There are none in parallel. They're just a whole entire array of series connected LEDs.
And they're what color? White?
They're red.
They're
red and orange.
Okay, so red ones will be a voltage of 1.5 volts each, and the orange ones will be about 1.8. So that times whatever the stack is.
192?
Yeah, something like that. It's in the 190 kind of range.
Is the dishwasher dirty dishes?
Was it big?
No.
Oh no, those. Actually, I don't know if I emptied it. I might not. I think those are
300.
Those are plenty.
Yeah, so that makes sense.
Don't worry about it. Okay, now we have ES1. Okay.
So if that's that the voltage is right. Now
Yeah.
if it's 25 milliamps a piece, and we have none connected in parallel, so we're not multiplying the amperage at all.
Right.
So it should be 25 milliamps that's driving the whole entire system, no? If it's all just series connected, or
Yeah. If it's all series connected, the current is the current through all of it.
so the current
right?
should be 25 then, and we're seeing 88.
You're seeing 88. What do you mean 25?
25 milliamps per LED.
Right.
Now,
Well-
if we're only creating a series connection throughout the whole panel of LEDs, that means we're not multiplying amperage at all, right?
Do you think there's a sine wave going to the LEDs? Do you have a rectifying diode or no? Or is
We're not using any diode there. We're just using the capacitor straight into the panel.
okay? And the panel's designed to take AC, right?
This panel, we just constructed this by hand.
Oh, okay.
So all we did was we took those LEDs and we made them a series connection all the way throughout
Right.
192.
But you
So
don't.
I mean, we should either be seeing a higher amperage, or we
But
should
you're
be
getting
seeing
you're getting light out of it, driving it with an AC source, though, right?
Yes.
Well, that's interesting. In its own right.
So that's why I would think that the small drop in amperage makes sense.
You don't have a photodiode amplifier, do you?
What was that?
You don't have a fast photodiode amplifier, so you could look at the light?
No.
No. Okay. Well, we're gonna turn this thing on in a second into a load, and see what's happening here. And
well, if you're using the 0.15 UF, you should be at a resonant frequency of somewhere around 2.1 kilohertz.
2.1. Okay.
Yeah, that should pretty much be the frequency, because this coil that we're running here, it pretty much matches the same thing that you guys have there.
Right. Okay. I'm moving this into view. I'm going to take this and go over here. Oh. What the heck is that? 2. So channel 4. Okay. Now. Whoa. But anyhow, he's done a curious thing, and he's combined microwave energy and electric fields.
You want some sellotape?
Yeah, huh?
You want some sellotape? Tape, sellotape.
Oh yeah. And all kinds makes things dance and merge, and a lot of people have taken an interest in his work, but for some reason he can't reproduce anything.
Why do you think that is?
I've never met the man. I've just seen a lot of videos.
Okay.
And like most of the videos that I've seen of most of these things, they don't show you a lot. And that's sort of unfortunate, because there has to be some evidence of a conscious measurement going on somewhere. And if he's not able to do that, I'm not sure what Hutch. I mean, Hutch. Have you ever watched the tapes of that guy?
Yeah, I have.
Yeah.
It's all over the map. So if there's any bloody electric field, you should see something.
Here, I'll watch this.
Are you watching it?
I'll watch if this one goes up.
Have you seen anything?
It's slightly above 0, but I don't know what that means.
Okay, now it's not. And I will take this, and I will go from here to here. Is it 0?
Yeah. Yep.
So that's where the other one would have been useful, because that one could actually measure electrostatically to 0. And these can't.
Daniel has this thing which measures fields somehow, and when he walks up, the meter goes up, and he walks like 20 feet away and it goes away.
Yeah, I've got one too. You want to see it?
I thought that's what you were trying to do here with this.
Yeah, this one. No movement, right?
No, it's still at 0.
Okay. Zero it. Open the aperture. Go this way. If I look at the plastic, I'll see an electrostatic field, because plastics always have some charge. There's neutral. There's the surface charge on the plastic. And at 2 inches away from here, at this opening, it's direct reading on surface voltage.
It's pretty amazing.
That's
Okay,
amazing.
so it's strictly an electrometer, right? So you can now. I'm going to get rid of this. Move that away. And you get to mend the books. All right. So what I did is I grounded the electrometer and I ungrounded it. Okay. Okay, so I'm 0. And what I want you to do is yeah, tip it toward you like that. Yeah, hold on to the handle. And 0 it.
Okay.
Right?
0.
Okay. Tell me if anything bloody moves. Yes, no, maybe.
No, not yet.
Because we've got 200 volts at the output of the coil. But you don't see anything, right?
Nope.
So there's no DC static voltage.
If I zero it out and at a different reference,
Yeah.
and then bring it down. You gotta get that on
What's the
camera.
point?
There.
There you go. Thank you.
There it is.
What's the point?
The point is that that these types of devices are all they're pieces of copper. They have remarkably interesting geometries to them, but there's something missing here. There's something missing, which is a transient field condition. There's a high frequency impulse function that should be going through there that isn't. That when you self-excite this thing, you can create a lot of voltage off of it because it's an inductor and it'll store energy and release it in a recoil, which is called flyback, right? And of course you can drive lots and lots of LEDs and get a lot of light out of them, in particular because there's the odd phenomenon that they get brighter, with high duty cycle, high currents, right?
And that's being made use of in industry already.
It's already being done. And as a matter of fact, this right here, 1, 2, 3, that right there. This is an amazing flashlight. This has got a small inductor in it, and it has a switching regulator in here that is pumping more and more current into this LED. Each time I switch this, it goes low, medium, high, right there. And these devices are industry standard types of chips. Linear Technology, Maxim, Texas Instruments, to name a few of them, are key producers of those parts. I use them all the time for LEDs and other purposes, but nonetheless, this exhibits the exact same principles as the LED drivers, and that is you store energy at coil, you let go of it, the voltage goes up. It's called a boost regulator or a boost converter, and in fact some of these things will do a buck boost where you can put 12 volts on it and it'll create any voltage from a high voltage down to a low voltage. So in that sense there's nothing unusual here because it's a coil. It's an odd geometry coil, but it's a coil. And if you follow it, there's always an open area in the center, and the mean diameter is this surround of wire, right? And it's just out of habit that looking at this thing on the videos that you sent, my estimation was something like 10 millihenries. It turned out to be about 11 and something millihenries. So in terms of dimensions and the amount of wire and how many turns and so on are in there, this follows all the standard rules that you would expect. But if there's something interesting about this that has the ability to influence the space around it, there has to be something else here besides just a piece of copper wire. Or we probably would have been doing this a long time. You know, I hate saying that, but it's because I know this has been done before. And there was more than a piece of wire. In fact, Hubbard talks about resonant frequency of the iron being up in this, what was it, 1.4 megahertz or a couple of megahertz or something like that. And that by pulsing the thing, he could tap into the magnetic energy of the iron. Henry Moray was doing a similar thing with his coils, causing bursts of energy transfer from one point to another and down converting higher frequencies. Perigo, Hendershot, and those types of arrangements, if you look at them, most of the magnetic field conditions were null field conditions, where the coil's a coil, but the coil doesn't have any inductance. And in fact, this thing right here is approaching that type of structure where you've got two bucking coils. And it's not the general field sense that you're looking at with these coils. It's the near field and the far field. Far field is zero. Near field, you have field conditions, right? So somewhere in between those 2 points is this little transition point where something like this, something like that, or the coils that Moray was using, or even Perigo, that creates a null field at some point, but near the coils, they have a field. Far from the coils, they have no field. And so I'm not sure how to rationalize how in the world this stuff works. But right now, the tests that we've done today, this behaves the way I kind of thought it was going to behave, which is we can get it very close to being unity, but then what we've got is a piece of wire inserted between the supply and the load, right? So, no big thing. It's a magnetic balun. What goes in comes out, and the only difference is that there's a time delay between the two, between what's on the beginning and the exit, and it may be that in a structure like this, it's that time delay in something else that allows this to produce an over unity effect. But I'm at a loss to explain it right now.
So have you seen the experiment with the neodymium magnet ball in that TED talk, where it's spinning and it's just when the positive pole hits one side of the circuit, the sensor detects that and then switches the circuit the other way.
Yeah.
So it basically creates like an electromagnetic bearing of sorts.
Yeah.
That's pulling the magnet around, so it will eventually run out.
Right.
But it's super efficient, so you can get it up to speed like 50,000 RPMs. They get them up to with these things.
Yep.
They get up to 100,000, but the ball would fall apart.
Okay.
And then they let go, and it just can keep going for ages.
Well,
and ages.
I work in this very mysterious place called the semiconductor industry, and there we have what are called turbo pumps, and the turbo pumps are what take a vacuum chamber from 10 to the minus 3, 10 to the minus 4 torr, and knock it all the way down to 10 to the minus 9, 10 to the minus 10.
You mean suck all the air out of it?
Suck all the air out. Literally, these things are spinning at 30 to 50,000 RPM on magnetic levitation bearings. There are no bearings. It's a magnetic field.
Okay.
And so you get these things spinning in a vacuum and turn them off. You can go home for the evening, come back the next morning, and they're still spinning.
Okay, so that's an old experiment.
Huh?
That's an old experiment.
Well, it's just tools that we use
Yeah.
because it's what you do for high vacuum chambers.
Okay.
Right? So,
Do you know the work of Smith that Lorenzo's always quoting?
who's this?
Someone Smith, Don Smith.
Don Smith.
Yeah, I've got a good video. I'll give it to you before I go if you like.
Okay. Yeah.
It's him standing up talking about his devices that he claims to have got over Unity from, but it's quite a different setup. It's more along the lines of this thing.
What's that? Like this?
Yeah.
Yeah.
Creating these.
You see, this is a funny thing, because when I first saw this, and if you look at the stuff by Carr, and you look at how the field enters this from the pole pieces that it moves through, the field goes through this way, through the flat side, out the flat side. It doesn't come around the periphery, right? So one of the things that you realize when you do that, when you couple in through here and here, is that the coupling coefficient, if you put a coil around the middle, you have a very high coupling coefficient. If you come in like this through the flat sections, or through the square section, if you want to call it that, you have a completely different coupling coefficient to this coil. And like all of the work that Tesla did, when the coupling coefficient was absolutely critically balanced, and an impulse came by like this moving through a magnet, all of the energy transfer was in one direction, none of it in reverse. And that was actually the trick to everything that Tesla did, was critical coupling and critical impedance matching. This is another one of those. And all of the stuff that was in Carr's literature that I've been able to read show this thing, and it also shows capacitors in between each one of these units also going through the magnetic field in that peripheral hub. You've seen this, right? And when I saw this thing for the first time, with the coupling coils around here around the equator, that doesn't replicate this. It doesn't replicate this field. So if you were actually going to replicate this field, then you'd put a coil this way around it, right?
Doesn't sound easy to.
You would put the coil literally at 45 degrees to this coil. And then you would size it in its diameter so that when you pulse that coil, the reaction in these coils was unidirectional. Right? You understand? And every time I see this thing being played with, they've already got the coils around this way, and it's the wrong way to put the coil. It should be going around here. Right? And it's a much bigger diameter. But
in all the drawings I've seen, there's no winding, there's no coil. No, there's
well,
nothing.
no, all the ones that I've seen they've got a coil right on.
Oh, you mean the actual photographs and stuff of people playing with it, right?
Yes.
Okay, the drawings that we've.
But the drawings have none of that.
No.
None of that at all. But if you look at the field execution in Carr's stuff, all of the fields go right this way through the coil and out here. And even though it's a fixed polar magnetic field, I don't know if they pulse that too, but if it's a fixed polar magnetic field, the induction into this coil is going to be emulated, if you're going to do that electronically, by a coil wrapped around this at 45 degrees.
Okay, so from a research and development standpoint, for the next step of our research and development in this direction of what Tesla and people who've tried to emulate his work suggest us to go toward, would you say working with something like this in order to demonstrate some kind of anomalous function or behavior, like we thought we were seeing in those, or I mean, do you think working on the theoretical groundwork inside of our present kind of electromagnetic physics to create the systems like you're describing, you're creating these fields.
You know, you can speculate
Lots.
either physically or engineering-wise, anything, and in fact model an awful lot. But to date, I haven't seen the results of all of that powerful thinking in a ambient extraction device. And you know, a lot of these people call these things free energy devices. It's a misnomer. It's not a free energy device. It's an ambient extraction device because you're trying to pull in energy from around the device that you're exercising so that it can produce more than what it's taking in on the direct excitation by influencing the space around it. This is this is the type of thing that hits you after you've looked at something long enough that it all assembles into a concise idea that something that you might even discover in a dream. But Dr. Petty always said that if you keep staring at the problem, if you keep surrounding yourself with information about the problem, eventually you'll solve the problem. But focusing directly on the problem, you may miss it because you're not allowing your mind to assemble the answer on its own. And right now, I've seen this stuff and I've read about just about every ambient extraction device that there is. And I can only see similar characteristics of all of them. And the similar characteristics are that they're transient devices. They are somehow absorbing energy from the space around them. And it's not, and in fact, in three of the devices, the current that came from the wires, they called it cold current because they were using wires that were significantly smaller than what was normal to carry currents of the size that they were measuring and illuminating lamps and so on with, particularly Moray. And who's the other one that did cold current? What was that?
Edwin Gray.
Is it Gray? Yeah, I think Gray was the other one that he said that the currents that were being utilized were able to go in large magnitude through exceptionally small wires. And it's as though there's not just the current of electrons going through the wire, but a current of external influences traveling along with it, right?
Yeah.
And that's where Floyd Sweet's work is sort of interesting, because if you bias the non-inductively wound coil, maybe what's happening is that in the pulsing of those coils from the side, that you not only get the current going in one direction, but you're also pulling in something adjacent to those wires in this bidirectional flow that you think is there, should be there. But all of the fields should cancel, but if you supply an external field, the fields of that folded wire are no longer valid. So maybe that's what's happening with Sweets. I don't know, because I haven't experimented with it enough. Because one of the things that I've learned is that experimenting with this stuff takes an enormous amount of time, and it doesn't pay the bills.
No.
So
Yeah, no.
doesn't pay the bills.
It costs you an extra supper as well.
Yeah. And the interesting thing about it is this is not the first time we've been playing around with this, and it won't be the last.
Good.
But it's a good exercise.
Yeah, I think so.
It's a very good exercise.
I think so. Yeah, I've been looking at different groups trying to work on this stuff, but like only on the phenomenology kind of side of things. I don't understand the theory. Just like, you know, does it work? Really, some groups with propellers and impellers and the geometry of those and things.
Yeah.
And it's been difficult to get like really on paper or in front of you working model, you know. But this group was, you know, really keen. The Abha Coil group. And Franklin's still working at his plans and stuff. Yeah, the cache.
You understand what I said about that 45-degree coil, right?
Yeah, exactly.
That has to be done.
Yeah.
Yeah.
There's two. The center one wasn't angled; it was just straight up and down. But the outer ones were at that.
At that 45-degree, yeah.
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 I've done.
This is beautiful, by the way. This
Yeah,
this
you
thing
did a
is
great
absolutely
job.
gorgeous.
Mm.
Yeah.
Tesla did, by the way, Tesla did a lot of these conical
Yeah, I saw.
coils. Yeah, you've seen the pictures of those. Yeah.
So do we still have the plans for Tesla's devices? Like, or have they all been made secret and destroyed?
I've heard
No.
he's
Well,
created 1,200 patents. but
no.
I've only
There's
seen like
121 patents.
300. Yeah.
111 are in the book,
Okay.
right? The other
Somebody mentions
10.
1,200 patents, and
no.
I never see
No.
the rest.
The other 10?
No.
Where's the other 10?
They're classified.
Really?
Yeah.
Okay.
Those are classified by the U.S. government. There's a number of I mean, a lot of stuff that Sweet was working on is classified. There's a lot of things that I guess a number of people have done have been classified.
Okay.
But Tesla, for all the information I've read on Tesla, there's 121 patents, of which in the published patents of Tesla, there's 111. Right?
In this,
You can buy that book. You've got that book?
no, not the complete patents.
No, I've got it out back there. And I've got all the patent wrappers, which is the patents in process.
From him.
No, from there was a guy up in Redwood City who used to publish them.
Oh.
He's gone now, but he did a very good job publishing everything he could on Tesla.
Sounds like you read it all.
I've got a shelf of that stuff about this wide.
Awesome.
Yeah.
Okay.
So it's just stuff that you research it because there's something in there that it's almost like you can feel that it's there.
Yeah.
You know it's there. You know that there was more to what he wrote than what he wrote. But reading between the lines is not always possible. And it's not always possible with most of these people. So it's, but maybe constant exposure over and over and over again, you get to that point where maybe there's a moment where you can see it all fit together, right? And I'm obviously not there yet, but maybe sometime.
Cool. Thank you very much.
All right.
Yeah. Thank you. Mate,
Get this mess out of here.
Can we help you? Can we help you put it in your store?
I'll have to think about how I'm going to.
The waveform. I just want to be able to pulse it at different frequencies. And I'm hoping we can smell it. The center. I gotta go get my tool bag. I'll be right back.
Mean.
Yeah, we were just testing out for frequency response of this coil with the meters and the pulse generators that Kirkwood had in his home, which are analog based, and they can are immune to a lot of like digital noise or any kind of digital processing that you would encounter. It's all analog based vacuum tubes. So pretty neat stuff. Those are they don't make them like that now. Maybe for high-end experiments, but so we were doing an impulse based on a schematic from Daniel, and then we were watching the response to see if there was any like over unity or output or something anomalous. That's not conventional. We did not see any of that. So what I'm trying to do now is just to pulse it. I'm not particularly looking for a specific frequency. I just want to be able to see if I could dial this in and see if I could smell that ozone he had produced at the blessing ceremony when he brought it over there. So that's what we're going to do.
Okay, could you talk a bit about how the first order and second order effects? Is it possible that we could be seeing over unity on a second order set of stuff, which is only possible to see when we're dealing with nonlinear experiments?
Definitely nonlinear will put you in a different category.
Of measurements?
Yeah.
Can you tell us a little bit about the problems, if you would just explain what Daniel's argument was, that because could you just tell us about it?
Okay, there's two things here. When you're just watching volts and amps with meters, whether they're RMS or not, you don't know how apart they are in phase with relative to each other, so you don't know what the true power requirements are, because they could be fully out of phase and have VARs instead of watts. And so the problem is trying to figure out how the waveforms, both amps and volts, are close together to see if it's producing usable watts. So meters, just digital voltmeters, won't give you that unless you have digital processing inside that can do that. And I guess the more expensive the meter, the more flexibility you'll have to see in that real time. Now that's digital, which again is immune to digital noise, and how I don't know if this is going to affect that through this circuitry. So it's just to take out all those kind of noise variables or radiation variables. You kind of, if you go analog, it's usually a best approach. I don't have those kind of meters, but what I do understand is that linear elements will react with standard electrical engineering terms. But when you start varying the parameters of capacitor inductors in time, and I'm talking about an inductance that's static, if you could make it dynamic, whether you spin it or you change its parameter internally by, say, putting something in series and parallel at twice the frequency of its fundamental, would create possibly an underdamped or overdamped situation depending on how you designed it. But what you're looking for is an underdamp so that it grows in time. So as you're storing energy in parallel, you're releasing it in series for capacitors, and the opposite for inductors. If you do that at twice the frequency, you're going to be transferring, from what I've understood in the literature, transferring energy at different frequency, from one frequency at a high frequency point to a lower frequency point, or the other way around. So you're shifting the energy in the time domain, which when you apply it to variable inductors and capacitors, you could transfer energy or amplify energy in that way, and that's what I'm looking for. But for that to happen, it needs to be dynamic elements varying in time with the voltage and amps from a source.
Okay, so yesterday we did not have instruments set up to measure in a nonlinear fashion over time.
No, we were driving everything with sinusoidal, very standard, very steady, very by the book kind of experiments. And I think what we got to do is find nonlinear doors or phenomenon in these things and exploit them so that we can extract energy from it. And it's true that if you can agitate your environment to the point where the environment pushes back into the system, that would be the ideal way of extracting energy, whether it's temperature or whether it's like electric or magnetic. One way to do that is when you do the nonlinear elements and you're varying at a rate of change that's not your standard dLdt or dCdt, or the variable of capacitors, very linear, or variable of inductors in a linear way. If you could do it non-linearly, then you introduce a derivative of the element which needs to be accounted for in the whole circuit. And when you do that, you can have second ordered or third order effects, and you have to see how that plays into the circuit with both voltage and currents produced by the elements as they change, and from the driving circuit that's getting that element to activate. So there's potential there for solid state generators that are not moving, but the elements are, parameters are changing in time.
Okay, so in order to set up an experiment that takes a series input and output and looks at things over time to get to these second parameters and third order parameters, third order phenomena, well, what should we set up? And would you be able to set up something like that? I mean, how would you set it up?
Well, you have two coils here. If you could, in one, you figure out its fundamental, whether it's in series or parallel. And then what you do is you switch series and parallel, series and parallel, series and parallel. And since this is in the kilohertz range, we should be able to get circuits to put the coils either in series or parallel with ideal diodes, which it's an active diode circuit arrangement where you can turn it on and it'll pass current either way, and then turn it off like an SCR and it'll stop. But it's both ways, and I could show you one. I have one from this company in San Francisco. But anyways, using 3 of those and then using 2 elements, you could put them in series and parallel at a frequency that you can control, and then you can send a signal out that's half of that frequency that you're series and paralleling the elements. That would, even though this is static, that would change this to a very dynamic element from twice the inductance when it's in series and half when it's in parallel. So that effect there could bring about that nonlinearity I'm looking for. I'm looking for nonlinear results by nonlinear stimulation, because everything else is by the book. You'll never see anything out of the ordinary if you do linear results. You know.
Okay, so if we set up the experiment as you've described, would you expect to see, I mean, and in what form would you expect to see some workable energy?
The voltage will grow over time. I don't know what the amps will do. I think that'll stay constant, but the voltage will keep increasing, and I don't know if the circuit will be able to handle it. So If anything, it'll just blow up within the first microseconds or milliseconds. I don't know. It depends on the fundamental and how fast you're driving it. But the way to get around that would be to put a spark gap and see that it tip over the energy. But what I'm looking for is underdamped energy production from variable elements in time. Nonlinear, and you can drive them into nonlinear dimensions, and then that in itself will play in other dimensions that we haven't looked at. Second order, third order effects of electric fields. What would that do to space around it? Or the magnetic field, second order and third order magnetic fields, what would that do to the space around it?
Okay, do you agree that the experiments that were set up do not demonstrate over unity at present? I mean, Daniel's claiming that he's lighting more than it's possible to light. Kirkwood was saying, you know, this is completely physically possible with all of our present understanding.
Yes, it's very standard what he's doing, and his load is nonlinear.
And he
it's a diode, so it's not going to be a linear response at all. If you drive into high amps by pulsing it at short duty cycles, yeah, you could drive it to illuminate more with pulsing as opposed to DC, and it's a nonlinear load. To simulate a nonlinear load on this system, you would need a nonlinear dynamic resistor. Or a resistor that's variable in time, so you could change it so that it becomes nonlinear how you want it when you pulse it at that frequency. If you could simulate the nonlinear characteristics of a diode with a resistor and emulate that and see if it truly does that, then yeah, it would
okay, so
be similar.
How can we set up this measurement of a non-linear setup? How can we get a non-linear load and measure it? This experiment that you gave us the example of, would that do the job?
That's already nonlinear because it's spinning in space, that inductor. The way to do this one would be to change inductance in time. So I guess you could say the nonlinear load here would be the variable inductance of this in time. Parallel and series of both coils.
So how can we do that?
I don't know from the top of my head. I would have to look at it. But I did mention how you can series and parallel something which is ideal diodes.
Okay.
Which is active O-ring of diodes.
Okay, so still it's inconclusive if there's over unity here.
I haven't seen physically myself the over unity. I do know that this thing puts out ozone when you drive it at from 20 to 50 volts, and the output is still in the hundreds of volts. I don't know where that's coming from. My speculation is the magnetic field intensity in the middle of this coil creates high magnetic stresses between nodes, enough to do a high voltage stress in the center to the space inside.
Okay, and Kirkwood says that's possible at low currents.
Okay.
Okay.
Yeah. So I don't know what it would take. I do know that you can do it with electrostatics, with a high voltage transformer, and doing it electrostatically, but we're using magnetic fields here to create a high magnetic stress field, causing, that in itself would cause high voltage stresses into the space around it if it's compact enough. And I just want to see if I could smell that right now.
Okay, let's see if we can do.
Okay. So, I'm not good with interviews.
You're very good.
Hey.
That's very good. So what you gonna do?
I'm going to provide power to this for now. Let's see. Plus here. And then I'll just put the load right in. This is a motor driver. I don't care about the waveform. I just want to see if I could smell the ozone at whatever voltage and current this thing's putting out. Okay, so I don't need those banana clips. Right. You have here.
Is that how you call them? Banana clips?
Yeah.
Uh-oh, that one goes right through all of them.
Okay, so this is minus.
I'll come back in a sec. Let's just get a see. I asked Kirkwood very clearly, does the computer... Oh yeah.
So we have electricity.
What have you got?
Electricity.
Yes.
Good.
Excellent. Okay, so we asked him, does it create, is it normal at low levels to have a field this concentrated so we can create ozone? He says, there's a dearth of published data relating to magnetic field-induced O3 generation. Calculation of the field geometry and differential magnitude gradient to affect the oxygen pairing from O3 is non-trivial and cannot be simply established in quantity as a loosely slated conditional normal at low levels. No, the situation is probably manifest in the central bore of one of these coils, but not at all an easily modelled parameter of an ionization threshold by any means. See what we're dealing with here. Okay, so I'll take that as a no. Otherwise they'd be doing it with low voltages all the time as opposed to really high voltages online. Okay.
It's not trivial. Well, let's read it again. So that way we can.
At the bottom there.
Bottom?
Yeah.
There's a dearth of published data relating to the magnetic field-induced O3 generation. Calculation of the field geometry and differential magnitude gradients to affect the oxygen pairing to form O3 is non-trivial and cannot be simply established in quantities as a loosely stated condition, normal at low levels. No, that situation is probably manifest in the central bore of one of these coils, but not at all an easy modeled parameter for ionization threshold by any means. So it's hard to do. It's hard to get O3 pairing with magnetic fields, and meaning that you would have to create high magnetic stresses, and to do that here with low voltage, low currents would be impossible. So if we can smell ozone at low voltage, low amps on these coils, there's again something new there to be explored and looked into.
Okay, cool, thank you.
So, can we just experiment? We came to this facility because it was open to the public today, and it's basically an electronic shop where people can come in and develop and test things. And it's
I know, that's what I'm asking. Sorry, just doing my white balance here.
yeah, and just people come here and work on electronics and try to go to seminars here, and it's open for people to come here and join and work on electronics.
It's an open source thing, is it?
I'm not sure, but we're having people bring out a amplifier that they'll send a signal through. Hopefully it'll do the voltage and amps we want to get that ozone smell out of it.
So what's the setup that they need to do? Yeah, because we don't want the circuit that Daniel explained. Can you remember?
the signal goes around like this, and at the ends it's open.
Even if that's
Okay. Yeah.
People will start the video, they'll see that, and they'll be like, oh, these things are great.
It's really a fear thing. I haven't gained up the courage to try to figure out straight from
I just noticed this creates a positive that's not necessarily true. It might be that it's just isolated from ground, so that you can. I actually run OS X, but right now I'm running Ubuntu because the other day I was doing something that you can't do in OS X. And Ubuntu is, a version of Linux that's really easy to install. Although actually now Ubuntu has gone, I don't know, they went crazy and it's terrible now. So now I actually run Linux Mint. But this is an old install, and it's hard to get 3 different operating systems to boot on the same Mac. So I'm not really going to change it until I have to. But yeah, I don't actually really run Ubuntu anymore. I run Linux Mint. But Linux is powerful because you can do anything you want without any arguing or fussing. And there's none of that stuff that Microsoft, Windows, or even Mac forces you to do just to make them happy. They're like, oh, you need to. I don't know. It's made by people with the same intentions, the same desires for a free world.
So open source, is there any open source framework of this electronic center? Is there a kind of ethos of open source? You guys
here at Noisebridge? Well, yeah, I think that people here are much more into open source than into closed source. The idea is that humanity was founded based on mutual aid. That's like why we have communication. If people were just fighting with each other all the time, we wouldn't need words. And the thing that evolved us and separated us from the animals that are just fighting for something is that we can work together. And open source is the concept that if I come up with an idea of how something works, and I can explain it and publish that for anybody who wants to use that for anything, then hopefully they won't use it for war, but instead we'll use it for cooperation, and we'll make the world a better place for all of us, for everybody.
Very exciting.
I can't believe you have this running on a light.
Well, this fluorescent light doesn't create. Yeah. If it's out of the sun, it's permanent. So it plugs straight into just had a DC power cord going.
Haha. What is it saying? It's saying linear methods. Never mind. Anyhow, we can't smell ozone. Our last test is to see if we can smell ozone. Daniel says, if you wind this up like a unification coil, then you can smell the ozone. Easy peasy, just turn it on. Get it into resonance at high voltage. Not that high compared to how much you need normally to get this, to get ozone, and you'll smell ozone. So that is an anomalous phenomena that we are trying to demonstrate. However, it's not set up to. It's not wrapped like a unification coil with extra windings and a Rodin spiral to concentrate the magnetic field. It's just wrapped like a single abha. So where was that 1830 where we got that?
600, 700, 800.
800 what?
Volts.
No way.
Yeah.
So you're generating 800 volts now. How come it's so much more? Oh, you're just measuring it properly.
Well, I'm just measuring where it should be open. Remember, he said.
Yeah. Okay.
I hear a slight tone.
I see.
But it's bouncing back and forth. It drops and increases, drops, decreases.
Okay, so unfortunately for us linear thinkers, the best demo that we're going to be able to get is perhaps when I get back to New York and Daniel wraps it up for me as a neutron. So the 500 the buckaroons. But yeah, then it should pour off ozone. People go, that's strange, that shouldn't happen at these temperatures. I don't mind looking like a fool. I'm pretty sure I have to.
Okay, this thing keeps increasing the higher the frequency we give it.
Really?
I say we keep going.
Yep. That sounded like going down. What are you at?
600.
600 volts. What's the current going through there? You don't have a measurement.
No, I'm not measuring current.
Okay, well what you got now?
It's bouncing up and down because it's modulating itself. I don't know why, but it's just modulating itself. It goes up and down to 8, 12, down to 6, 2. There's a sweet spot around. Let's see how far down.
I reckon 1830.
Yeah.
That's pretty stable. What's your volt levels? 500, 700, 6.5, that's down 8, 8, 7, 8, 6, 7.
It's about 19.44.
6, 7. What's 19.44? That's the signal.
Yeah, 19.6.
7, 5, 6. This one 8, 8, 7, 8, 8, 8. Yeah, that's good. 5, 7.
That's 500 volts per division. Oh, I guess it could go up to 2,000, 4,000 maybe.
Okay.
That's 100 times probe we're using. It's fixed. So
So, smelling any ozone?
I'm not sure.
definitely has an effect.
I keep thinking there's a slight wind coming up.
I'm not smelling anything like that. We'll wait till we get to the upper part. I mean the unification. Waves, nonlinear, and sinusoidals, curvy waves, which you'd think are less linear. Why are they linear?
Well, you carry more frequencies with a square wave than with a sinusoidal. Harmonics. We get higher voltage when we do square waves on the output, or the open open windings for this. Oh, you don't with a sinusoidal. Sorry, I'm sorry. We're definitely introducing harmonics and this thing seems to respond with square wave better than without it, with sinusoidal. There's a sweet spot around 20 kilohertz. It starts ringing again. Getting hot? No.
Can we put some Beethoven to it?
You could do anything you want.
This isn't a magnet, surely. It doesn't move at all. Okay, can we try some Beethoven?
Yeah.
Okay. With Kirkwood, and what is your Japanese friend doing?
Kirkwood, we had a sinusoidal, and the frequency was different, I believe, but the fundamental that we're hitting could have been subharmonic of the actual frequency. Anyways, we're pulsing it harder now with square waves, and it's introducing a lot of harmonics, and we find a sweet spot around 19 kilohertz, 19.1, 9.2, and it starts ringing again at that frequency. You could hear it, but the voltage also increases to 800 volt peak. That's just what I'm reading directly from from it.
Okay, and your friend in Japan, what does he say he's doing to get more volts out than his model predicts?
He takes inductors or a transformer and he pulls them hard so that he introduces second and third order effects in the magnetic field, and when it collapses and comes back into the system, he notices higher voltage than what the model says, and the only way he can account for that is the rate of change that he's driving these things. But he's also in his papers that I forwarded to you guys, he's varying the inductance to get it to work. I don't know how he's doing it now, but he's saying that he gets the second and third order effect,